Hello and welcome to the Complete SQL Bootcamp. We'll be working with one of the most popular and in-demand versions of SQL, PostgreSQL. But the syntax and skills you learn in this course can be applied to any other major database or software that uses SQL. Hello everyone, and welcome to the Database Overview lecture. So in this lecture, we're going to learn what are databases and why use databases. And after we answer those two fundamental questions, we'll get a sense of where this course fits in the realm of things. So let's start off with a basic definition. Databases are systems that allow users to store and organize data. And they're useful when dealing with large amounts of data. So what are our database platform options? Well, there's actually lots of database platform options, a lot more than what I put here, but here are some of the main ones. You have PostgreSQL, you have things such as MySQL, and MySQL Server Express, Microsoft Access, and then SQLite. Each of these has their pros and cons, but we're going to be focusing on PostgreSQL. The reason for this is because PostgreSQL is free, it's open source, it's widely used on the internet, it's multi-platform, so meaning if you have various operating systems, like Windows or Mac users, you can all use PostgreSQL. So PostgreSQL is a great database choice for learning how to use SQL. And SQL is a structured query language, that's what it stands for, and it's what we're going to learn in this course. SQL is going to be the way we communicate for a database. It's the way we're going to be able to communicate with the database to get data out of it or put data into it. And the SQL learned in this course can be applied to a variety of databases or SQL-based software. So we're not going to pigeonhole ourselves to just PostgreSQL. What you learn in this course, you're going to be able to apply it to a variety of databases or software that uses SQL. Hello everyone, and welcome to the SQL Fundamentals section of the course. This section is going to focus on SQL syntax. And what's really important about what you're going to learn here is that the syntax in this section can be applied to any. Hello everyone, and welcome to the SQL Fundamentals section of the course. This section is going to focus on SQL syntax. And what's really important about what you're going to learn here is that the syntax in this section can be applied to any major type of SQL database. Let's go ahead and get started. Welcome everyone to this lecture on the select statement. Select is the most common statement used in SQL, and it fundamentally allows us to retrieve information from a table that exists within a database. Later on, we're going to be learning about how to combine the select statement with other statements to perform more complex queries. So what's the actual example syntax for a select statement? Well, after opening up the query editor, what we're going to write for our most basic select statement is select column name from table name. And you'll notice that in general, we capitalize the SQL keywords. This actually isn't 100% necessary. SQL will still run even if you don't capitalize these, but it makes it much easier to read what are the fundamental SQL syntax statements versus what are the column names or table names that you're yourself editing, depending on what you actually want. So the most basic syntax here is we choose a column name from a table. So let's see how this actually works within PostgreSQL. So we already know that we have a database, and then we right-click on that database and we open up that query editor. In our case, it will be the example DVD rental database. And so the way PostgreSQL operates is inside of this database, you're going to have some number of tables. Here we have an example of 3 tables. And recall then each of these tables is essentially like a spreadsheet. We have columns and then rows of data. And here I've just made up some data. So each of these tables has columns 1, 2, and 3, so C1, C2, C3, and then rows of made up information. When we actually say select column name from table name, PostgreSQL essentially reads this a little bit backwards. It first has to decide what table you're referencing. It already knows what database you're referencing because that's how you open the query editor on that database. So it takes a look at what table name you're looking at, and then it's going to take a look at the corresponding column name. So, for example, we could say select C1 from table 1, and it would look something like this. It's actually grabbing column 1, and it'll return back that entire column, and X, Y, and Z. If we want to select multiple columns from a table, we can say column 1, comma, column 2, etc. You just separate out the column names by a comma. And keep in mind, these don't need to be in order. So if you only wanted column 1 and column 3, you would just say select the names of your columns separated by commas, and then from the table you want them in. If you actually want all the columns from a table, you can use an asterisk symbol, in order to request all the columns from a table, essentially just asking for the entire table back. So you'll say select, an asterisk, and then from table. In general, it's not good practice to use an asterisk unless you actually want every single thing in that table. And what's going to happen here is if you use the asterisk in the select statement, it's going to automatically query everything, which increases traffic between the database server and the application, which can slow down the retrieval of results. So you should really only be using that syntax if you actually want the entire table back with all the columns in it. If you only need certain columns, do your best to only query for those columns. Let's go ahead and walk through some examples in our DVD rental database to get some practice with these basic select statements. I'm going to open up pgadmin. All right, so I've opened up pgadmin. I'm going to click down on servers. Note that I have different versions of PostgreSQL installed on this computer. Go ahead and choose the one that you installed for your computer. I'll go ahead and choose PostgreSQL 12 since that's what we'll restore DVD rental on. I've now connected to that server under PostgreSQL 12, and now I want to query the particular database inside that server. So that's going to be DVD rental. I right click, and then I'm going to open up the query tool. I take a look at the query tool and I have the query editor as well as the data output. So let's practice our very first query to this database. So if you're ever curious of what tables are actually available to you in your database, what you can do is underneath DVD rental, you can open up schemas. You'll see there's a public schema, keep going down, and you'll see there's tables here. And you can expand on tables, and I'll show you the various tables available to you inside of this database. And you can check out the resources for this lecture or the previous lectures. We actually have a mapping of those tables and the relationships between them. We'll talk a lot more about joining tables together and also programmatically asking a database what tables are within it. But right now, we'll just do this through the pgadmin graphical interface. So I can see there's 15 tables here. And if we click on one of these tables, we can later on see what columns are available, etc. So let's go ahead and start by asking for an entire table back, or all the columns in a table. I say select, and then I type in an asterisk there, from, and then we'll say actor, semicolon. And then I'll go ahead and run this. And if you're on Windows, you can choose F5 to quickly run that. And you'll notice that it has the data output. I'm going to kind of move this over so we can see this. And we can see here it has the actor ID, the first name, the last name, and then the last update. And we can scroll down here and see the various results. So again, this returns back all the columns. If I only want a single column, let's say I only wanted the first name, then I just look at the column name, which is first underscore name, say first underscore name, and then I'll go ahead and run that. And now I only get back the first name. If I want the first and last name, I would take a look at those column names, which I can always refer to over here on the side. Last name's available there, and then run that. Okay, so I can see first name and last name, and keep in mind, they actually don't need to be in any sort of order. If I wanted the last name to show up first, I could say last name, comma, first name, run that, and it would show me in the order I requested. The last name column showing up first, and then the first name. Everything's linked here by what row. So we can see Penelope Guinness, Nick Wahlberg, etc. Now a few more points I want to show you is that you notice that I capitalized the SQL syntax keywords, but even if these were all lowercase, select, and then I put from in all lowercase, and I run this, it will actually still work. It's the same thing. However, it's much easier to read, and it's just standardized notation if we just do this in all caps, and then I can quickly realize if I'm coming back to this that select and from are the keywords. And notice pgadmin also highlights them for us. You'll also notice that I have a semicolon here. The semicolon is to denote the end of a query, but if you delete that semicolon and still run this, you'll notice it works just fine. So things like capitalizing those SQL keywords as well as adding in that semicolon really helps as far as readability is concerned, especially if you're going to be sharing these SQL queries with someone else. It can read very clearly where this actual query is meant to end, as well as what commands you're actually using. You can use the scratchpad here if you want to kind of play around with things later on as our SQL queries get more complex, you may want to work a little bit on the scratch pad. And I'm going to zoom out just so we can see this clearly. There is a query history that you can click here, and you can see the various query histories. And then you can always copy them, or you can copy them directly to the query editor. So for example, if we come back here, maybe to select first name from actor, I could say copy to query editor, and it jumps back to the query editor, and I can see select first name from actor is already there for me. All right. And then if I wanted to, I could run this and edit it in any way I want. So I can just double click here and start editing for another table. Maybe I want all the columns from another table. Let's say select everything from city, semicolon, hit F5, which is essentially a refresh for running this. And we can see here city ID, city, country ID, last update. Okay, so those are the very basics of the select statements. Coming up next, we're going to have just a few challenges to make sure you understood all this. I'll see you at the next lecture. Welcome back, everyone, to this lecture on select distinct. Sometimes a table contains a column that has duplicate values, and you may find yourself in a situation where you only want to list the unique or distinct values in that column. The distinct keyword can be used to return only the distinct values in a column. The distinct keyword operates on a column, so that means the syntax looks like this. We say select, and then distinct right in front of whatever column we're interested in grabbing the unique or distinct values from, and then we'll specify what table this column is in. Sometimes, to clarify which column distinct is being applied to, you could also add in parentheses for clarity. So note that distinct on a column works with or without parentheses. This is what it would look like with parentheses. And again, it will work without parentheses as well. Later on, when we learn about adding more calls, such as a count call and a distinct call together, some sort of parentheses structure will actually be necessary to clarify what is actually being called on what. But we're going to see that in a future lecture. Let's first think about what does it actually mean to call distinct on a column. Imagine a table of people who were surveyed to choose a color. So here we have the names of the person, just their first name, and then the color choice they made. Let's imagine we actually called select distinct from the name column from the color table. Well, notice that we have two instances of David inside this name column, which means when we actually select the distinct names from this table, it's going to return back the following, just the unique first names in this actual column. Keep in mind that given the previous example, we don't really know if the person of the name David was a duplicate entry who happened to change their color choice later on as the same person, or if it was two different people that happened to have the same first name. Calling distinct on this particular column just answer the question, what are the unique first names that are there in that table or in that column? It probably makes more sense to ask how many types of unique color choices were there. So what we can do is say select distinct choice from the color table, and here we have all the distinct or unique color options that were chosen. Let's go ahead and see a couple more cases of when distinct would be useful. We're going to jump over to PG Admin. All right, here I am at the query editor. What I'm going to do is first explore the film table, and there's different ways I can do this. So this is a pretty small database. I could either expand on this film table to see what columns are available, film ID, I could scroll over here, title, description, or I could just say the following, select everything from film. And it's okay to do this since this is basically kind of a toy database and toy table. It's not going to be huge. So we'll go ahead and just run that. And we can see here we have the film ID, the title, description, release year, language ID, and I can keep scrolling to see other information and other columns that are available inside of this film table. So let's think about what kind of questions distinct can help answer. Distinct really helps when we want to know the unique values inside of a column. And if we take a look at these actual tables here, something we may want to know are how many different release years do we have inside of this film database? And what we can do here is say select distinct, and I'll put it in all caps since we're treating it as a SQL keyword. You can see it's highlighted as such. And then we'll call it on release underscore year from film. So if I run this, what's happening here is it's going to return back just 2006. So this quickly answers the question, how many unique release years do we have inside this film table? And it ends up we just have 1. All of these films were released in 2006. If we take a look back at this, it should also note that we can add in parentheses. And we can see here that it's directly connected to distinct. And if we run this, we'll get back the exact same result. And for some people, this is more legible, coming back to their old SQL queries. It works either way, so it's really up to you if you want to use parentheses or not. Let's come back and take a look at the entire table again, just so we can check out the columns. You'll notice here we have the release year. Something else that's interesting are the rental rates. And it does look like we had different numeric rental rates. So some movies rent for $4.99, some rent for 99 cents, others rent for $2.99. Distinct can help us answer the question, how many unique rental rates do we have? What we can do then is just say select distinct, and with or without parentheses, we can say on rental rate. We'll go ahead and run this. And here we can see that we have 3 distinct rental rates, essentially a low tier at 99 cents, $2.99, and $4.99. Later on, we'll be learning how to actually sort these or order them based off a certain value. But right now, PostgreSQL just returns back information as efficiently as possible. So you may actually get these in a different order depending on your operating system. All right, that's it for the lecture on Select Distinct. Coming up next, we're going to quickly test your new skills by giving you a quick little challenge on Select Distinct. I'll see you there. Welcome everyone to this lecture on the count function. The count function returns the number of input rows that match a specific condition of a query. We can apply count on a specific column or just pass count and then an asterisk. We will soon see this should return the same result because count is merely reporting back the number of rows returned, which is going to be the same regardless of what actual column you're looking at. Let's see a simple example. Here again we have that table with a couple of names and then their color choice. Let's imagine we called select count name from table. Notice here count does need the parentheses because it's a function acting on something. So it won't work without the parentheses. Keep that in mind. If we were to count the number of names from table, that's just asking for how many rows are there in the name column, which is going to be 4. So the result will be count 4. So again, it's simply returning the number of rows in the table. In fact, this should really be the same regardless of the column we call, because each column has the same number of rows since they're literally in the same table. Which is why, whether you call select count name from table, select count choice from table, or select count asterisk, which is just saying select the count of all the rows for all the columns in the table, they should all return the same thing. Since the original table has 4 rows, that means each column has 4 rows, which is why you usually just see an asterisk from the table. Now keep in mind, it's sometimes useful to use a column name instead of just providing an asterisk, because if you come back on your SQL query sometime later, it may actually help kind of stir the memory of what actual question you were trying to answer. So again, because of this, count by itself simply returns back a count of the number of rows in a table. And count is usually much more useful when combined with other commands, such as the distinct command that we already learned about. Imagine we wanted to know how many unique names are there in the table. So, to answer this question, we need to first decide the distinct number of names. Then we'll provide count on that result of distinct name from table. So the logic that's going to happen is distinct is going to figure out what the distinct names are. Here it sees that David is duplicated, so it's just going to kind of remove that, and now we have the 3 unique names, and then count is going to count the remaining rows here, which in this case is going to be 3 rows. So the end result for select count distinct name from table is 3, answering the question that there are 3 unique names in the table. It won't tell you what those names are. That would just be a distinct call by itself. And again, notice the parentheses structure here. It's informing us that we are calling count on the result of distinct name. If you want, you can also provide parentheses for name on distinct, although that's not necessary as we previously discussed. However, some people find this result more readable. Let's go ahead and explore some examples in pgadmin. Okay, here I am at the query editor in pgadmin. Let's select everything from the payment table just so we can take a look at it. So we'll say select everything from payment, and I can see there's a payment ID, customer ID, staff ID, etc. There's also an amount and a payment date. Let's imagine I just wanted to know the number of rows that are in this table. Now, luckily for us, this table is pretty small, which means I could, if I wanted to, scroll all the way down and then check the actual here on the left-hand column. It's just a count. So I could scroll all the way down and eventually I would see the correct answer. However, and this is actually quite a large table. There's more than 1,000 entries. In a realistic database, you're going to have very, very large tables. So you're not going to be able to just scroll down just to see how many rows there are in this table. So one easy way to do this is just say select, count, and then to make it easier to read, I'll pass in the parentheses, and it just is asking count the number of rows in all the columns. So those should all be the same, which means it's going to be 14,596 rows. So much easier to do that than scroll down until you see 14,596. And you could do this for essentially any column. So if I pass in the, let's say, amount column, again, this is just asking how many rows are there in the amount column. Well, it should be the same as the number of rows in the actual table. So notice we get back the exact same result. So when people are beginning to learn about SQL, they sometimes get confused over what column we're going to pass into count. And in the end, it really doesn't matter. It's really probably most common to see an asterisk since, again, it doesn't matter. But sometimes it might be easier to use a column name in order to set your mindset as far as what you were thinking when you were writing this query. So if you come back later in time and you would see this query, you can see that you were probably thinking about the amount column because somebody asked you a specific question of it. So keep that in mind. It might be easier for you to actually clarify with a column name. Okay, now let's go ahead and say, just select the amount column from payment, run this, and I can see there's different amounts that people are paying, $7.99, $1.99, $2.99, $5.99, etc. Let's imagine I wanted to figure out the actual number of payment types. What are the actual number of unique amounts or distinct amounts being paid? If I were to just use distinct on the amount column, I would run this and it shows me the distinct values, $1.99, $10.99, $2.99, etc. Essentially removing any duplicates. So this answers the question, what are the unique payment amounts? However, my question is, how many unique amounts are there? Which means I should be counting the result of this. So one way I could do that is scroll all the way down and realize there's 19 rows here. Or to do this programmatically, I would just say count distinct amount. I run this and notice here, when I'm using these two functions, I will need to specify with parentheses. So I'll say count distinct amount, and then it actually ends up working. So the reason in this case that I need to use parentheses is because if I don't, PostgreSQL is going to think that I'm trying to call count on some distinct column, which doesn't exist. So this is why I need to call parentheses and specify that distinct amount should happen first before I call count on whatever this result is. And if you want, you can add in another set of parentheses just to make it more readable for you. It really depends on your personal style. And we'll get back the same result. Okay, so that's it for learning about count. Coming up next, we're going to learn about the select where statement, which is really going to help us out in a lot of different query types. I'll see you there. Welcome back, everyone, to this lecture on the select where statement. In part 1, we're just going to be learning the basic syntax structure, and then in part 2, we'll actually jump over to pgadmin and code out some examples. So the select and where statements are really the most fundamental SQL statements, and you're going to find yourself using them in almost every SQL query you do. So the where statement allows us to specify conditions on columns for the rows to be returned. The basic syntax would look something like this. We decide on what columns we want back, so we'll say select column 1, column 2, etc. And then we decide what table we want those columns from, and then after that, we can describe conditions. So we'll say where, and then some manner of conditions. So let's actually go into detail of what those conditions are like. The where clause appears immediately after that from clause of the select statement. And then the conditions are used to filter the rows returned from the select statement. And PostgreSQL provides a variety of standard operators to construct those conditions. And I want to make it clear that the conditions we show here are available in any major SQL engine. So it's not just unique to PostgreSQL. So we first have the comparison operators. And the comparison operators allow us to compare a column value to something, essentially allowing us to answer questions or queries such as, where is the price greater than $3? Or where is the pet's name equal to Sam? So those kind of statements of greater than or equal to or less than, those are the comparison operators. And you're probably familiar with the base syntax operators, at least the operator syntax signs, because they're just basic math. So, for example, if we want to check for equality, we just use the equal sign. Then we also have the greater than and less than sign, the greater than and equal to signs, and then even the not equal to. And there's two ways of doing not equal to in PostgreSQL. You can have a less than and greater than sign right next to each other, or the more common way is to do an exclamation mark and then an equal sign. In addition to those, we have the logical operators, and that allows us to combine multiple comparison operators or effect comparison operators. So you're also probably familiar with these ideas of and, or, and not, and they essentially allow you to use multiple comparison operators. So you can do something like condition 1 has to be true and condition 2 has to be true, or condition 1 is true or condition 2 is true. And then you have the not operator, which essentially means the opposite of whatever condition you're specifying. So where this condition is not true. So let's actually walk through the very basic syntax of what this would look like. And we'll do this with the example table we saw before, where we have some names and some color choices. So in order to get back both columns from the table, we could just say something like select the name, choice columns from table. So now let's try to get only the people named David. So there's a condition there where I want the name column to be equal to the string David. So the way I do this is I say select the name column and the choice column from table where name is equal to David. And note here in PostgreSQL we use single quotes in order to denote these strings. And also when we're checking for equality here, the capitalization does matter. Also keep in mind that I selected both the name and the choice column here. I could, if I wanted to, just select the name column from table where name is equal to David, and then I would just get back the entries on the name column. So it's not terribly useful. So keep in mind you're probably going to ask for more than just a column where you're filtering these conditions on, just as asking for name and choice. Let's imagine I wanted to do multiple conditions. So previously I have two Davids here where we have green and red. I can use those logical operators such as the AND keyword to test for multiple conditions. So here I'm grabbing the name and choice column from this table where the name is equal to David and the choice is equal to red, returning back this single row where both those conditions have to be true. Okay, let's go ahead and see you in the next lecture in part 2 where we jump to pgadmin and work through a bunch of examples available to us inside the DVD rental database. I'll see you there. Welcome back everyone to the Select Where Part 2 lecture where we're going to head straight to pgadmin and code along with a couple of examples just to give you an idea of the different use cases for select, where, as well as comparison operators and logical operators. Alright, let's begin by exploring the customer table. I'm going to just select everything from the customer table so we can explore it quickly. We'll say select and then asterisk from customer, semicolon. Go ahead and run this. And I can see there's a customer ID column, a store ID, first name, last name, email, an address ID, some active Boolean, whether or not that customer is active or not, so true or false, the date they were created, last update, and then also an integer corresponding to the active Boolean, so ones and zeros for the trues and falses here. Okay, so what can we do here to start filtering out customer information? Well, maybe something I want to know is who has the first name Jared? Maybe someone comes to the store and asks me, I'm looking for some customer named Jared. So I can say select all the columns from customer. We'll go ahead and delete that semicolon. And then we'll say where, and this is where we have a condition. So we have to say the column name. In our case, it's first name. So we'll scroll over here. You can see we have first underscore name. So we'll say where first underscore name is equal to, and then single quote, capital J, and then Jared. Note how the single quotes are essentially automatically ended for you in PostgreSQL and pgadmin, semicolon, optional if you want to end this or not. We'll go ahead and run this, and now I can see I have that information for Jared. Now let's go ahead and explore the film table to see how we can combine conditions with logical operators. So we'll say select everything from film, run that, and it looks like I have different film IDs that are unique to each film, a title for each film, a description, a release year, a language ID, rental duration, rental rate, length, etc. So let's start playing around with this. Let's go ahead and find maybe all the rental rates that are higher than $4. Recall that when we use distinct, there's really only 3 rental rates, 99 cents, $2.99, and $4.99. So I can say select everything from film where the rental rate is greater than, let's just say 4. Semicolon, go ahead and run that. And now I can see all the results that are back here are now $4.99, $4.99, etc. So they're all greater than $4. And let's go ahead and add another condition on this. So we can do this for logical operator. Let's go ahead and choose ones that are expensive to replace. Notice we also have a replacement cost. Let's go ahead and choose the ones that have a replacement cost greater than or equal to $19.99. So we'll say and notice I don't need to rewrite where again. So the where just applies to all these conditions that I can keep linking together with logical operator. So well, rental rate is greater than 4 and let's say replacement cost is greater than or equal to $19.99. And because these are numeric types, I can directly compare them to these numbers. Note how PostgreSQL lets you know what data type it is. So there's different colors depending if I'm working with strings, whether these are keywords in PostgreSQL or whether they're numerics. We'll go ahead and run this. And now I can see here that we have $4.99 and then the more expensive movies to replace, $19.99, $28.99, etc. And I can keep tacking on more and more. So maybe I want only certain ratings. Maybe I only want the R movies. So you can always remove that semicolon and continue on another line where we say and then maybe rating is equal to, and in single quotes, R. Go ahead and run that. And now we keep filtering more and more on this, etc. And recall that here we're just asking for all the columns, but I can always just ask for only certain columns. So I can say select the title from film. And then we run this, and essentially I get a list of all the titles where these 3 conditions happen to be true, where the rental rate's more than 4, the replacement cost is greater than or equal to $19.99, and the rating is equal to R. Let's imagine I want to answer the question of how many titles there are where these conditions all happen to be true. Well, what I can do is simply add in a count. So I can either count title, which is essentially counting how many rows are returned here. So if I run this, it gives me back that there's 34 movies where all these conditions happen to be true. But if you remember from the count lecture, I can really pass in any column to this. Or in fact, I can just write an asterisk here, which essentially just count the number of rows that are returned from the film table that satisfy these conditions. And if I run this, I'll always get back the same number. So recall from that count lecture, it doesn't really matter what actual column I apply here because I'm really just asking the question here, how many rows are returned that satisfy these particular conditions? Let's go ahead and explore a quick example of the OR logical operator. Maybe I only want movies that have an R rating or a PG-13 rating. Well, what I can do for that is I can say where rating is equal to R, or make sure we spell this right, rating is equal to PG-13. Notice here I'm still counting the number of movies returned here. I run this and there's 418 movies that satisfy either the R condition or PG-13. Now remember, we also have the not equal to operator in case I want everything that isn't an R movie, for example. I could say something like the following. I could say where the rating is not equal to R. And let's just go ahead and grab all the columns here so we can see the results. We'll go ahead and run this. And if I scroll over to the right, you'll notice on the rating that everything here is everything that's not R. So that's G, PG, PG-13, NC-17, etc. So we have all the ratings here, but none of these are actually going to then be R. All right, so that's it for these code along examples. Coming up next, we're going to check your understanding by giving you a couple of challenges with these select where statements. Hopefully you can already tell this is a very powerful tool and something you'll be using quite often when it comes to your SQL queries. I'll see you in the next lecture. Welcome back, everyone, to this lecture on order by. You may have noticed that PostgreSQL sometimes returns the same request query results in a different order, meaning you may have run the exact same query on your computer and saw the results in a slightly different order than what I have on my computer. So, in order to alleviate this issue, if we want the results in a certain order, we can use the order by to sort rows based on a column value in either ascending or descending order. So that would be alphabetical for string-based columns or numerical order for numeric columns. The basic syntax for an order by statement would be as follows. We select whatever columns we want from the table, and then we decide to order by a specific column. And then optionally, you can add in ASC or DESC, whether you want that ordering or sorting to be ascending or descending. Notice the order by towards the end of the query, since we want to do any selection and filtering first before finally sorting. So that means order by is going to be towards the bottom of a query and one of the very last things that SQL actually performs. So we're going to do all our selection, all our filtering. If we use a where statement, that should come before the order by, and then right at the end, we'll go ahead and do any sorting. And you use ASC to sort in ascending order, DESC to sort in descending order. If you leave it blank, order by just uses ascending by default. Now what's also interesting is you can use order by on multiple columns. So this makes sense when one column has duplicate entries. Let's take a look at this example database or example table really. We have 3 columns here, company, name, and the sales for that individual at that company. Notice here that we have duplicate entries under company. So if we were to actually order by 2 columns here, we could select the company column, the name column, and the sales column in that order from this table, and then we order by company and then order by sales. What does that actually mean? Well, it means we sort everything first based off the company column. So notice we have Apple coming in first in alphabetical order, then Google, and then Xerox. And then the corresponding names also get lined up. However, we can then also order by the sales. So after you've done the sorting based off the company column, which makes sense because there's duplicate values there, within that particular company, we do a second ordering, which is by the sales column. So note the sales now is in an ascending order for each individual within the same company. So we see Andrew with 100 and then Zach with 300. And then for Google, we see Claire with 200 and then David with 500. So if you have duplicate values in a particular column and you want to sort not just by that particular column, but another column as well, it makes sense to do an order by with multiple columns. And it's going to sort based off the order you provide. So it'll order by company first and then by sales. Let's go ahead and explore some more examples in pgadmin on the DVD rental database. Okay, here I am inside of pgadmin. What I'm going to do is explore the customer table. So we will say select, and let's select just everything from the customer table so we can take a quick look at what the results look like here. So notice we have this customer ID, and more or less it seems to be in order except for this first one, which is 524. And then we also have the first name and last name. Let's see if we can order everything based off the first name of the user. So that would be an alphabetical order based off first name. So what we do here is towards the bottom, we'll say order by, and then we decide on the column. So we'll say order by first name. If I don't leave anything here and just run this, it'll automatically order it here in ascending order. So starting at A all the way down. So then if you start going more and more down, you'll eventually see B's and then C's. This is the same as if I had clarified ascending order. So you may be wondering why bother clarifying ascending order there. Well, it's nice because if you come back to read this or someone else is reading your code, you can realize that they specifically wanted it in ascending order. We can do the same for descending order by adding in DESC towards the end of this order by statement. And now notice we're starting at Zachary, then Yvonne, Yolanda, and going down. So starting at Z and then going down all the way to A. Now notice here that we have different store IDs and we also have duplicate store IDs. So we have store ID 1, store ID 2, and store ID shows up multiple times. So we have multiple entries for store ID, which basically means that this particular customer, let's say Zachary Height, goes to store ID number 1. And this second customer, Yvonne Watkins, goes to store ID number 2. So there's Yolanda, Wilma, etc. What we could do is first order by the store ID to get all the results per store and then organize it by first name. So the way this would work is I would say first order by store ID. And if I just run this by itself, notice now I get store ID 1 first. And then if I were to continue scrolling here, it's maybe a couple thousand, so it might be hard to actually see this. But then I eventually get store ID number 2. And then within this, you'll notice that if we scroll back up here, I'm actually just going to select store ID, first name, and last name columns. So let's reduce this a little bit. We'll say select the store ID column, select the first name column, and select the last name column. Run this. So if we take a look at this, the store ID is now sorted starting at 1, and then eventually scroll down, you'll see store number 2. But the actual entries themselves are in no particular order within store ID. So what I could do is say first order by store ID, which makes sense because there's duplicate values in that particular column, and then go ahead and order by first name. So after you order by the store ID, go ahead and order by first name, run that, and here we can now see store ID number 1, then everything starting in alphabetical order based off the first name, and then we scroll down here to eventually hit store ID number 2, and we can see within store ID number 2, all the first names are now in alphabetical order, starting with A. And if you want, you can always add in ascending and descending to each particular order by statement. So I could say order the store ID on descending while ordering based off first name on ascending. And notice here, semicolon is optional. So we run this, and now at the very top, we're starting at store ID number 2, and then seeing the alphabetical order, Aaron, etc. And then eventually, if I scroll down far enough, I would see store ID number 1. The other thing to note here is that if I select just first name and last name and run this, it will still work, which means I can technically sort by columns that I do not actually request in my select statement. Now, whether or not you actually want to do that in a real world setting is really up to you. Typically, it would make sense to actually select the column you're ordering by because that just logically looks better as a result, and it'll kind of continue the logic of your SQL query into your results, and you'll understand whatever the person was trying to explore from a business standpoint. But I do want you to be aware of the fact that you can technically order by a column and not select it in your select statement if for some reason you want to do that. Okay, that's it for the order by lecture. Coming up next, we're going to quickly discuss a limit function, which allows us to actually limit the amount of rows that are returned in a query, and then we'll give you some challenges for the order by statement in conjunction with the limit statement. I'll see you at the next lecture. Welcome back, everyone, to this lecture discussion on the limit keyword. The limit command allows us to limit the number of rows returned for a query. It's useful for not wanting to return every single row in a table, but only view maybe the top few rows to get an idea of the table layout. Limit also becomes extremely useful in combination with the order by statement that we just learned about. Limit goes at the very bottom end of a query request and is the last command to be executed, because essentially what the limit does is after you're done filtering with the where statement, ordering with order by and sorting, and any other sort of conditions or any filters you want to do in a query, the limit is just going to say, all right, how many rows do you want at the end of the day? So let's learn the basic syntax of limit through some examples. This should be pretty straightforward, and you should really be thinking about this in conjunction with order by in order to answer certain business questions. Let's jump over to PG Admin. Okay, here we are in PG Admin. Let's go ahead and explore this payment table again. First, what we could do is just select everything from the payment table. So I can say select everything from payment, and I get this variety of payment IDs, customer IDs, staff ID, rental ID, etc. And then I also get a payment date, which is a timestamp without a time zone. It's actually just a day and then the hour, minute, and then second and milliseconds where this payment actually occurred. What we could do is order by this payment date in order to see either the oldest payments or the most recent payments. So what I could do is say select everything from payment and then say order by payment date. And if we run this on a timestamp, what's going to happen if we refresh this? Notice we get 2007-02-14. So this is in American formatting, meaning it's year, month, and then day. And if I want, I can either order this by default ascending to get 2007 to and then 14, or I could say descending, run this, and I see 2007-5-14, essentially 14th of May instead of 14th of February. So what this actually means is I can use order by in conjunction with limit to get the top n rows of something. So for example, I can answer the business question, what were the 10 most recent purchases in the payment table? So after I conduct my order by, I call in the limit keyword and then provide how many rows do I actually want. So if I just say 5, you'll notice here that right now it's returning everything if I scroll down here. If I say 5, run this, I keep scrolling down, but I only get 5 rows. So essentially what this answers is what were the 5 most recent rows or payments based off the payment date. So we can see the payment date here, and right now we're returning the 5 most recent payments. So this will allow you to get the top n of anything based off some column. So what we do here is just order by some column and then limit it to the top n results that we want. And it's up to you whether you want to do ascending or descending, depending on the actual data type that we're looking at. So we can see here, in fact, some of these payment amounts were zeros. So what I could end up doing is also filtering it where the amount isn't 0. So we can start to get really nice complex queries here. So I can say select everything from the payment table, saying select all the columns from this payment table. And then right here, we're limiting it to the top 5 most recent ones based off payment date in descending order. So starting from most recent, descending to the historical data. And I could also then say where amount is not equal to 0. So we run this, and now I can see the 5 most recent payments where there was actually a monetary transaction and it wasn't just a $0 amount. So this is where we start to see much more realistic SQL queries. Given just the few commands we know, we can already answer lots of business questions. We can, in this case, select everything from the most 5 recent payments where the amount wasn't 0. All right. So hopefully that gives you an idea of the power of limit. And sometimes if you want, you can simply do something like select everything from payment limit 1 to just quickly get an idea of what this table actually looks like. This would show you what data types there are, such as integers, small integers, timestamps, etc., and an example of what these actually look like. So some people like to quickly run this sort of command in order to just see the general layout of a table. Okay, so that's it for this lecture on limit. It's a pretty straightforward thing. Limit just comes at the end, and you can limit the number of rows returned. Very useful in conjunction of order by. So let's test your skills in the next lecture where we talk about some order by challenges. I'll see you there. Welcome back everyone to this lecture on the between keyword operator. The between operator can be used to match a value against a range of values. So for example, we can ask where is a value between a low and a high? And this is essentially going to be a condition you can tag along with a where statement. You should note that using the between operator is essentially the same as asking individually where a value is greater than or equal to low and a value is less than or equal to high. So note that the low and the high here are both inclusive. So it's actually including the endpoints there. You can also combine the between keyword with the not logical operator, essentially asking where is the value not between low and high. And this is the same as asking value less than low or value greater than high. Note here that we are exclusive of the actual low point and high point. So what I mean by that is for the not between statement, if you're saying something like value not between 8 and 9, if a value happens to be 8, it's not going to be included in the not between. Versus, if we take a look back at the between statement, that is inclusive, meaning if you wanted a value between 8 and 9, it would actually include 8s and 9s there. So keep that in mind. And if you want to change exclusivity versus inclusivity, you can just go back and use the AND operator and then specify less than or equal to manually yourself with the comparison operators. Now, the between operator can also be used with dates. You should note that you need to format dates, in this case, in the ISO 8601 standard format, which is essentially just 4 numbers for the year, a dash, then 2 numbers for the month, a dash, and then 2 numbers for the date, or the actual day. So that means it would look something like, where is the date between, and then as a string with single quotes in that particular format, year, dash, month, dash, day, and then the other date. Something to keep in mind is when using the between operator with dates that also include timestamp information, so not just the actual day, but also the hour, minutes, and seconds, you should pay careful attention to using the between operator, especially since we have that issue of inclusivity versus exclusivity of the not between. So you should take into account the fact that a date time, that is both the date and the actual time information, would start at 0-100 hours. So that may have an effect depending on what the actual situation is and whether you want inclusivity or exclusivity around that midnight time or 0-100 hour time. Later on, we're going to study more specific methods to actually work with date time information types. So don't worry about it too much right now. It's just something to keep in mind for the future. Let's go ahead and get some quick practice with the between operator in pgadmin. Okay, here we are at pgadmin. What I'm first going to do is check out the payment table, since that's what we're going to be working with. For our examples, we'll say select from payment table. We'll grab everything, but just limit it to just a few rows so we can see the general syntax here and general columns. So the payment ID, customer ID, staff ID, rental ID, and then the amount and the payment date. So we're going to be working with these 2 columns here. Let's go ahead and see if we can use between on the amount column. Let's imagine we wanted to know the actual number of payments that were done between $8 and $9. So what we can do is say select from payments where amount between 8 and 9. If I just run this, it'll give me all the results. We can see everything here is $8.99. And if I actually wanted to know the total number of transactions, I can just count the number of rows returned, and it's 439 rows. If I wanted to know the opposite, essentially everything that wasn't between $8 and $9, I can simply add not between 8 and 9. I can run this, and then I get the number of payments that were not between $8 and $9. Let's take a look again now at the payment date column. So what we can do is, let's imagine I wanted all the payments that happened on the first half of February of 2007. What I could do is, let's just select everything so we can get an idea of what's happening here. Now we'll say where the payment date column is between, and what we're going to do here is make sure we format this correctly, which is going to be the year dash the month dash, let's say 01, and we'll say 2007 dash 02, and then the 15th. So we run this here, and we can see all these payments happen between the 1st of February 2007 and the 15th of February 2007. Now, something to keep in mind, especially when you're dealing with timestamp information, is that this timestamp information includes both the date and hour, minutes, etc. So that means PostgreSQL essentially has to decide, does a day start at 0-100 hours or at 2400 hours? And if you're dealing with exclusivity versus inclusivity, that actually might affect your logic. So what I mean by that is take a look at the results here. They all actually happened on the 14th. So if you kind of scroll down, you'll see there's 27 rows, and essentially all the payments that happen between the 1st and the 15th all happened on the 14th. Now let's actually switch this to be all the payment dates from the 1st to the 14th. And this is where students often get confused. They would actually expect to see these results. But if I run this, you'll notice nothing gets returned. And that's because when we're dealing with this end date, it's actually only going up to the 0-100 hour mark. It's not going to the end, which would be the 2400 hour mark of the 14th. which is why for these sort of between statements, when you're dealing with timestamp information, you just have to be careful of that. So you always want to double check and make sure you're getting the results that you expected. So in this case, I'd have to go all the way to the 15th to actually include information that happened on the day of the 14th. Okay. And later on, we're going to learn a lot more about how to deal with timestamp information such as this. So that's it for the between examples. Coming up next, we're going to learn about a couple more SQL keywords that are very helpful in different types of queries. I'll see you there. Welcome back, everyone, to this lecture on the in operator. In certain cases, you want to check for multiple possible value options. For example, if a user's name shows up in a list of known names. So instead of having to write a bunch of or statements, such as name is equal to David, or name is equal to Claire, or name is equal to Zach, we could use the in operator to just create a condition that quickly checks to see if a value is included in a list of multiple options. So you can check something like where name in Zach, David, and Claire. So the general syntax will be something like this: value in, and then a bunch of options. So, for example, an example query could be select the color column from table where color in red, blue. So note here that the options are in this little list in parentheses, and then we use the in operator to basically specify that we're checking for the color condition that happens to be either red or blue. So these are a bunch of or statements. So anything red and anything blue will be returned to us. And we can always expand this to more options quickly. So we can say, now where the color is red or blue or green. So essentially there's a little or statement in between all of these. Keep in mind you can also combine this with the not operator to essentially do this excluding these values. So where color is not in red or blue. It's essentially every color that is not red or blue. Let's go ahead and quickly see some examples in pgadmin. Here we are at the query editor. I'm going to take a look at the payment column or a payment table. Well, let's just select everything from payments. Let's just limit this to 2 rows so we can take a look at the result here. And notice we have an amount column. Let's first figure out what are the actual distinct values that are available to me in the amount column. So what are the unique amounts that we're charging? So we can say distinct amount from payments, and I'm not going to limit this since I want everything back. I run this and I can see I have $10.99, $1.99, etc. And what I could also do, just for clarity, is order this by amount, as we've seen before, and now I can order amount 0, 99, etc. So maybe I want to figure out all the orders that happen to be 99 cents, 198, and 199. So how could I do that? Well, what I could do is I could select any columns I want or everything from payment, and then we'll say where the amount is in, and here we'll go ahead and specify 99 cents, 198, 199. Note here that I'm not using strings or quotes because this is a numeric data type. So if we go ahead and run this, we get back a bunch of values where the amounts happen to be in 199, 99 cents, or later on 198. And if I wanted to figure out how many payments actually occurred that happened to be one of these 3 values, I could run this and I get back that there were 3,301 payments. Now let's imagine I wanted the actual opposite information. I wanted to count out how many payments were not 99 cents, $1.98, or $1.99. Well, there's a couple things I have to do here. First, notice here again I have the parentheses of that list of options. If I just add not in front of this and run this, then I get back the amount that is not in 99 cents, 198, and 199. So there's 11,295 payments that are not these 3 values. And let's go ahead and explore this on a string column to finish this off. We'll just say select everything from customer. Take a quick look at this. I have the first name and last name. So let's go ahead and select all the columns from customer where the first name is in, and let's just give some options like John, Jake, and Julie. We'll go ahead and run this. And here I can see there was no one named Jake in this particular table, but we did have a Julie and we did have a John. Okay. So that's the way the in operator works. Main things to keep in mind is that you're using parentheses here and then commas to separate out your options. And your options should be matching the general syntax of the column. So we want to make sure that for numerics, we're providing numerics in the list, and for strings, we're providing these single quote strings here. And we can always say not in if we wanted to see essentially the exact opposite. All right, that's it for this lecture. I'll see you at the next one. Welcome everyone to this section on group by. In this section, we're going to be discussing group by and aggregate functions. Group by is a SQL statement that will allow us to aggregate data and apply functions to better understand how data is distributed per category. In this section, we're first going to begin by discussing aggregate functions without any group by applications. Then, we'll learn about group by. With part 1, we'll just discuss the theory behind it. And then in part 2, we'll actually show you some implementation of group by statements in pgadmin with pgsql. Now we'll discuss the having call, which is going to allow for filtering in conjunction with a group by statement. Let's get started. I'll see you at the next lecture. Welcome back, everyone. Before we discuss group by operations, we should understand aggregate functions in general. SQL provides a variety of aggregate functions, and PostgreSQL is no exception to that. And all the functions we see here are available in any major SQL engine. The main idea behind an aggregate function is to take multiple inputs and return a single output. Now, PostgreSQL provides many different types of aggregate functions, but we're just going to discuss the most common aggregation functions in this particular lecture. The most common aggregate functions are average, which returns the average value or mean value. There's count, which we're actually already familiar with. It returns the number of values or rows returned. Then there's max and min, which return maximum and minimum respectively. And then there's sum, which returns the sum of all the values. So it adds everything up in that particular column. Keep in mind that aggregate function calls happen only in the select clause or the having clause. We don't know about the having clause quite yet, but we're going to learn about it later on in this section. Some special notes to keep in mind for certain particular aggregate functions is the average call returns a floating point value many decimal places long. So for example, it could be something like 2.342418, etc. And you can use the round function on top of average to specify precision after the decimal. So we'll see that in this particular lecture. And keep in mind that count simply returns the number of rows, which means by convention we could just use count asterisk in order to see the number of rows. We can either pass in a specific column or just an asterisk since it's essentially the same thing. But we've already discussed that before. Let's go ahead and see some examples of aggregate functions in our own database. And head over to pgadmin now. All right, let's begin by exploring the film table since we'll be using that. So we'll say select everything from film. And if we run this, we can see we have a film ID, title, description, and then release year, language ID, and we also have this replacement cost. Notice we have several values here. Let's imagine right off the bat, I wanted to know what the minimum replacement cost was. Well, what I could do is call my aggregate function, and then I'm going to call parentheses, since this is a function call, and I call it on that column, replacement cost. And when I run this, it's going to return back the minimum replacement cost. So at a minimum, we're going to have to spend $9.99 to replace a certain film. Now that also means certain films are more expensive. So maybe we have a budgeting question asking what's the most we can expect to pay to replace a film. In that case, we can just call max and figure out the maximum replacement cost. So the maximum replacement cost now reported back is $29.99. So that is the min and max function, pretty self-explanatory, and you can call them just on any column here. Keep in mind, if we were to try to call something else, like let's say I also wanted to call a film ID column for some reason, that doesn't really make sense. And the reason for that is we're just actually calling an aggregate function on a column, which means max replacement cost just returns a single value. So it doesn't really make sense to call another column with this. In order to call other columns, we'll have to learn about the group by statement, which is coming up next. So keep that in mind. When you're doing just simple calls or queries like this, where we want to figure out the min or max, it doesn't really make sense to call other columns there, since we're aggregating a bunch of values to just a single value. What you could do is something like min replacement cost from film, and we run this, and that works. And the reason this works is because that function maximum and this function minimum are both returning a singular value. So this will be the max and min for your replacement costs. So keep in mind, because those rows happen to match up, that sort of query makes sense. Okay, let's explore the other aggregate functions we talked about. We're already familiar with count, which essentially is counting the number of rows returned. So we can say select count in asterisk, run that, and that returns back how many rows we have. So we have 1,000 films. And keep in mind, this works on any column. So we could also say film ID, and that's essentially the same thing. Since that's the case, by convention, we typically just write an asterisk there. And we're already familiar with count. Let's imagine we wanted to know the average replacement cost. What I could do is say average replacement cost, run that, and that's going to grab the mean or average from the film table. However, you probably noticed it looks a little strange here, and that's because by default, this average call gives you a lot of significant digits. So if we expand this column, notice how I'm stretching it out here, we can see that it's actually 19.984 and then a bunch of zeros. So realistically, you probably don't want all of these significant digits past the decimal point. So what we can do is wrap this around with a round function, and the round function actually takes in two parameters. One is the value you actually want to round, and then we're going to put a comma here and how many decimal places we want to round it to. So we'll say to 2 decimal places. And this is essentially a mathematical call on this result. So it's going to take this result and then round it to just 2 places past a decimal. And then when I run this, notice I get back $19.98 as the average replacement cost from the film. And we can always edit this if for some reason we wanted 3 decimal places. We can run that and it keeps going. If I said 4, as you may have guessed, it'll start including the 0. So you can either stretch out this column to see all the results if you don't have that rounding call, or realistically, you're probably going to want to round this to some degree. Again, notice how round uses parentheses in order to organize its parameters or its inputs. Here we have the input that we're trying to round, and then the second parameter is how many decimal places. So we discussed average, count, max, and min, and then we finally have sum, which is going to sum all the values in a column. So what does that actually mean? If we take a look at our table again, select everything from film, let's imagine for some reason we had to replace every single film. So we were opening a duplicate store and had to replace every single film. So we needed to figure out the total sum of the replacement cost column. What we can do is say sum replacement cost. We run this, and it would cost us $19,984 to replace all those movies. And if we think about this value for a second, it actually makes perfect sense. Recall that when we were taking the average replacement cost, it was 19.984. And here, we're replacing 1,000 movies with the average replacement cost, so which means the sum of the replacement cost should equal the average times the actual amount of movies we have. So that's essentially 19.984 times 1,000 movies, which means, again, the total cost to replace all the films would be $19,984. All right. So those are the aggregate functions by themselves. That's average, count, max, min, and sum. You can hit the slides and check out the link for more complex aggregate functions, some of them which we will go over in later lectures. But right now, these are really the most common ones you should know right off the bat. And coming up next, we're going to see how we can use this in conjunction with group by to create very powerful queries. I'll see you at the next lecture. Welcome back, everyone, to part 1 of our lecture series of group by. Group by allows us to aggregate columns per some category. Let's first explore this idea of a simple example, and then we'll go over the SQL syntax. Let's imagine we have the following table. We have some sort of category column. Here we have A's, B's, and C's, and then some data value associated with them, such as 10, 5, 2, etc. We can imagine that maybe the category here stands for some sort of company, and the data value is how much we sold to that company. So we had one deal of $10 for company A. Later on, we had a $5 deal for company A, then a $2 deal for company B, and so on. So when we're actually performing a group by, there's a couple of key things to consider. The first is this category column. We need to choose a categorical column to perform the group by on. That is to say, categorical columns are non-continuous, or at least we're treating them as non-continuous for the sake of the group by. Now, something to keep in mind is these can actually still be numerical, such as cabin class categories on a ship, class 1, 2, 3, and so on. And you should also keep in mind that they actually may appear continuous, but you could treat them as a category. For example, if you recall to our DB rental database, we have different rental rates available, such as 99 cents, $1.99, $2.99, etc. We could treat each of those rental rates as its own separate class or own separate category. So just because something is being treated as categorical doesn't necessarily mean it's non-numeric. And we're going to see different examples of that in the next lecture when we actually program out in SQL some group by statements. But let's first go through the idea of what a group by actually does and how it relates to aggregate function calls. So the way a group by operates is the following. We have already chosen our categorical column. Then what we're going to do is essentially split this table up on a per category basis. So we have everything that went with category A, then B, then C. And then we have the corresponding data values. Recall that an aggregate function takes in multiple values and reduces them back down to one single value, such as the sum function can take in all these values per category or grouped by category and then return back their sum. So the total sum of sales to category A was 15, 6 to B, and then 18 to C. And we could do this with any of the aggregate functions that we just learned about. For example, we could take the average data value per category, 7.5, 3, and 9. We can even do something like a count per category. In this case, there was 2 rows per category, so they're all the same, 2, 2, and 2. So let's actually explore the general syntax. So the most basic group by call looks like this. We select some sort of category column or something we've deemed to be categorical, and then we choose to perform some aggregate function on the data column. So AGG here is just some placeholder for some aggregate function on some data column. We select it from the table, and then immediately after that, we call group by that category column. So the group by clause must appear right after a from statement or right after a where statement. So if you want, before you do the group by, you can filter things out using a where statement. So here we see just grouping everything together by the category. But if we wanted to, before we actually execute that group by, we could have done a where statement, essentially saying something like where category column is not equal to A, essentially ignoring all the A categories before we went ahead and did the group by. So the thing to keep in mind is the group by either has to come directly after a from statement or directly after a where statement. Now, one of the most important things to realize when learning about group by is the following. In the actual select statement, columns must either have an aggregate function call on them or be themselves in the group by call. So what does that actually mean? This is where beginners often get tripped up in learning about group by, so pay close attention to this one. So if we're using a group by statement, then if we're selecting that particular column just by itself, it must be included in the group by statement. So notice here, I've decided to select the category column, then that particular column must also appear in the group by statement. The only exception to this is if I'm calling some sort of aggregate function on the column itself. So in this case, because I'm aggregating something on the data column, it does not need to be included in the group by statement. So let's imagine a different example. We can have something like select company, division, and then sum of sales. So you can imagine we had 3 columns in this table. One were different companies, and then the divisions within that company, and then different sales per division per company. So what we're doing here is, again, notice that if I'm selecting a column, such as company and division, then they must also appear in the group by statement. So that means we can group by multiple columns, and we essentially just decide the order to group by in a very similar fashion that we decided the ordering of different columns when we learn about the order by statement. So again, here I'm selecting column and division. Since they don't have an aggregate function, they must appear in the group by clause. Notice again, the sales doesn't appear in the group by statement, which means it must have an aggregate function associated with it. So essentially what this is returning is the total sum of sales per division per company. And keep in mind that the where statements should not refer to the aggregation result. So you shouldn't be trying to do any filtering using a where statement on sum of sales in this case. Later on, we are going to learn how to do that using the having statement to filter on those results. But for right now, if you are using a where statement in conjunction with group by, that where statement shouldn't make a reference to what is being aggregated, such as sum of sales. That is what the having statement is for, that we're going to learn about later. So notice what we're doing here is we're saying select company division sum of sales from finance table, where division is in marketing and transport, essentially filtering out the divisions before we actually perform the group by on the company and division. And again, notice here, company and division appear in the group by. Sales does not because it has the aggregate function associated with it. Here's another example that if you want to sort the results based on the aggregate, you have to make sure to reference the entire function. So in a simpler example here, let's say we wanted to sum the sales, total sales per company. Then we could select company, sum of those sales from the table. We will group by company. And then the other thing to notice here is if I actually wanted to order by the sum of sales, I don't just say order by sales. I have to say order by the sum of sales. So notice that whatever I'm ordering by, that total statement should exist somewhere in that select clause. And then you could add something like limit 5, which would essentially show you kind of the top 5 sales or bottom 5 sales, depending if you did ascending or descending order per company. All right. So I know we just went over a lot of this, and it's best learned through practice. So I'll see you in part 2 in the next lecture, where we actually practice on our own DVD rental database. I'll see you there. Welcome everyone to part 2 of our lecture series on the group by statement. Let's go ahead and jump to our database and work through some group by examples so we can actually build in some practice into creating a query that would work with a group by clause. I'm going to head straight to pgadmin. All right, here I am at pgadmin. First, what I'm going to do is explore the payment table. I'm going to do this just by saying select everything from the payment table. Typically we wouldn't do this, but since we have a small table here, it's not so bad to just explore it. It looks like the payment table will have a payment ID, so it's a unique identifier per each payment. Then we have a customer ID. So notice here, it's categorical. So even though this is a number, this is essentially the actual customer ID. So this is customer 341, and you can see he's visited multiple times and rented out multiple things. And he had different interactions with different staff. So we also have a staff ID, which is also a numeric, but we can treat it as a class. Since it's a kind of a category here, we can think of this almost as the name of the staff person. In the same way, we can think of customer ID as here we have kind of a named identifier per customer. Then we have the rental ID here, essentially what movie was actually rented. Later on, we'll learn how to join this rental ID column to the actual film column to see what actual film is being rented. And then we have the amount on that particular transaction as well as the payment date. So let's do the simplest group by possible, which is to group together the actual customer IDs. So what does that actually mean? Well, I could say select customer ID from payment, group by customer ID. So if I run this, this is actually essentially the same thing as selecting the distinct customer IDs. This is a bit of a roundabout way to go about it. But if you think what we're doing here, we're just kind of aggregating all the customer IDs together. And we're not performing any aggregate functions on any other columns, so we just get this list of customer IDs. And if I wanted to, I could add an order by statement here to order by that same column. And essentially, I just get the customer IDs here that we have in the payment table in order. So nothing too crazy here. And this is not a typical use case for a group by, but it's the simplest group by possible of just selecting a column and then grouping by it, which is actually the same as essentially selecting the distinct values of that column. What's probably more helpful is to do this in conjunction with an aggregate function on another column. Let's imagine I wanted to answer the question, what customer is spending the most money in total? Well, what I could do is take the sum of the amount column in conjunction with grouping by customer ID. So if I run this, I can now see the total sum that every customer spent. And then if I wanted to actually order this, I would say order by, and I can't just say order by amount. I have to say order by the sum amount. So that is truly what this column is. It's not just the amount column. It's a total sum of the amount column per customer ID. And a lot of times that the word per really helps beginners understand what the group by is doing. So I can read this as the total sum amount per customer ID. And I'm going to run this, and now I can see this is in order. And we can change it from ascending to descending if we want with ASC or DESC. And this is a very typical SQL query that is using group by to answer a real question. What customer ID is actually spending the most amount of money? And we can do other things like actually count the number of transactions they're having. So I could do something like this. Instead of actually saying, take the sum of the amounts, actually just count how many transactions they're having. So notice here the difference in the question. Sum is asking for the total amount of dollars being transacted. Count is just how many transactions are occurring. So when I run this, I can see the count here with customer ID 148 having 45 total transactions. Okay. Now what we can also do here is use group by on multiple columns. So we discussed this, but let's go ahead and see it in practice. I'm going to first quickly show you the entire table again so we can get an idea of it. So again, we have that payment ID, customer ID. Notice there's also a staff ID. So what I could start to explore is grouping by customer ID and then grouping by staff ID, or grouping by staff ID and then grouping by customer ID. So let's go ahead and show you an example of that. I'm going to say select customer ID, staff ID, and then some amount. And I'm going to group by staff ID and then customer ID. So if I just run this, what's happening here is it's telling me the total amount spent per staff per customer. So that means customer number 1 spent $60.85 with the staff ID person number 1. And what I could do if I wanted to is order by the customer ID. So when I run this, I can now essentially see how much each customer spent with each staff member. So in this case, it looks like customer 1 spent $60.85 with staff ID number 1, and then $53.85 with staff ID number 2. Something to keep in mind here is while the group by order does matter as far as how you're grouping things together, the actual select statement, that order doesn't really matter. So I could, if I wanted to, organize the results by staff ID first and then by customer ID. So if we just see those results, I'll go ahead and remove the order by just so we can see those raw results here. But here, I'm essentially not changing any information. So we still see staff ID, customer ID, and then the total sum per customer. And then if you wanted to, you could either order by staff ID, run that, and I can see all the ones here. And then we could kind of do a sub-ordering by customer ID. And so I can see staff ID 1, and then there's transactions with 1. Staff ID 1 is transactions with 2, etc. Or I could order by customer ID, run that. And now notice I see customer ID is ordered, but it's ordered and centered here in the middle. So keep that in mind. All of these are essentially showing you the same information, but it's up to you how you actually want to display it. So most often, you're going to actually select things in the same order that you're grouping by in. So keep that in mind. And then ordering by, it's up to you depending on what kind of question you're trying to answer. So we could have also said order by sum on the amount column. Run that, and we get back these results. You can order by any of these 3 columns or multiple columns. But the main thing to note here is that I can group by multiple columns. Okay. The last thing I want to point out, and we will learn about this in much more detail later, is when you do a group by on a date column. So if we take a look at select everything from payment, notice that we had a payment date, which was a timestamp. Because it's a timestamp, it not just has the date information, but the time as well. So it has the hour, the minutes, the seconds, etc. So if we actually want to perform a group by a date, we have to call a specialized date function to convert the timestamp to a date, and then we can actually group by that. So what I'm going to show you is that function first. We can say select date from payment date, and we will learn a lot more about dealing with timestamps later on. But if we just run this, we can expand this column, and notice here, it's essentially just filtered out the actual date. It's removed that timestamp information, which makes sense because we don't want to group by every single transaction per minute. What we probably want to do is just group by day. So I'm going to say select the date on the actual payment date timestamp, which is essentially just the day from payment. And then let's go ahead and group by date, payment date. If I run this, this is essentially just returning back the distinct dates, but maybe I want to figure out how much is actually being processed each day. So I could take the sum of the amount column, run that as well, and then maybe I want to order by the actual sum amount column, run that, and I can see the days where we're having the least amount in total dollar transactions, or depending how I sort this, if I sort it in descending order, I can see the dates that we're having the most in dollar transactions. Again, what this date function is doing is it's extracting just the day portion from that timestamp information. Because if you just said group by payment date, the main thing to keep in mind is I don't want to just group by that payment date because it was a timestamp information down to the sub-second, which means I would essentially almost have a unique category per payment, which isn't terribly useful. However, we did have multiple payments on the same day, which is why I'm using date to extract just the actual year, month, and day information from payment date, which then means I can group by that. All right. So we've seen a couple of examples here already with using group by. What I want to do is give you a couple of challenge tasks. And these challenge tasks are probably going to be a bit harder than what you've encountered before because we are making a bit more of a leap in learning about group by as far as what operations and queries we are now capable of. So keep that in mind. These challenges won't be as simple as the ones we saw before, but hopefully they give you a good run for your money. All right. I'll see you at the next lecture where we present the group by challenges. Welcome back, everyone. In this lecture, we're going to discuss the having clause. The having clause allows us to filter after an aggregation has already taken place. So it comes after a group by call. Let's take a look back at one of our previous examples. Let's imagine this very simple query where we're selecting some sort of company column and then taking the sum of the sales column from some financial table where we group by company. So we're aggregating sales per company. Now we've already seen we can filter before executing the group by with a where statement. For example, here I could put a where right before my group by and say where company not equal to Google because maybe I don't want to include Google in my final results. So that's okay because the company isn't being aggregated in any sort of way. It is in the group by statement. However, it's not having an aggregate function being called on it. So I can use where. But what if we actually wanted to filter based off the sum sales? So keep in mind that since we're calling sum on sales, that's not going to happen until after that group by statement is executed all the way at the bottom, which means we cannot use where to filter based off aggregate results because those happen after the actual where statement is executed. So if after performing the group by and calculating the sum of sales per company, I wanted to then perform an additional filter on that result based off the sum of sales, I could add the having clause. So having allows us to use the aggregate result as a filter along with a group by. So you can essentially think of this as a where statement, but only for something that is being aggregated through the group by. And hopefully you can see that connection quite clearly here. So again, here I'm able to now filter based off the aggregate result of sum of sales in my having clause. So here I'm saying, do the filter of the where, and then after you group by, go ahead and do another filtering where we're having the sum of sales greater than some number like $1,000. All right, let's explore some examples of having in our own database. And then jump to pgadmin now. All right, here I am at pgadmin. I'm going to work through a very similar example that we just made up. Let's first check out our payment table. So select everything from payment, go ahead and run this. And we're already familiar with this. We have the customer ID, staff ID, etc. Let's go ahead and take the total sum amounts for a customer. So we'll say, select the customer ID and then take the sum amount from payments, and we'll group this by customer ID. So we can run this, and this all works out fine. I already know that if I, for some reason, wanted to filter out certain customers, I could say something like this, where customer ID, and maybe I wanted to say not equal to, or I could say something like not in some list of IDs. Like, let's go ahead and remove 184, 87, and 477. We run this again, and no problem. You saw that now those no longer exist here in the results. Now, what I cannot do is filter with a where statement on some amount, because the sum of the amount's not going to happen until after I call the group by. So what I'm going to do then, let's go ahead and remove this where example to simplify things. I can say after the group by, having some amounts, and let's just say greater than 100. So we go ahead and run this, and we can check out the results here. And now you'll notice everything's been filtered, so all the sums are now greater than 100. You should also notice, just like when we were using order by with an aggregate function on a column, we have to actually specify some amount. We don't just say amount. Let's explore using having with a count call instead of just a sum call. We can do this by maybe exploring the customer table. Just to remind you, we'll select everything from customer table. So this is the customer ID, a store ID, first name, last name, their email, address ID, etc. So what we can do here is, let's imagine we wanted to know the number of customers per store. What I could do is, if we scroll over here, grab the store ID and then count the number of customer IDs associated with them after I group by store ID. So we're going to say store ID and then count customer ID from customer after I group by store ID. We run this, and I can see the total count of customers per store. Keep in mind, I don't have to actually pass in customer ID, because this is just saying how many rows are there per store ID. So I could put an asterisk here, run this again, and you'll notice I get back the exact same results. Now let's imagine I wanted to select only stores that had more than 300 customers. Well, in this case, I'd have to filter based off something that's already been aggregated. So I can't do that with where, but I can do it with having. So I can say having a count, asterisk, greater than, let's say, 300, and that's essentially performing the filter after the group by. And keep in mind, depending on how you want to think about this, you can switch out an asterisk there for customer ID, and it will perform the exact same. So customer ID, run this, we get back the exact same results. It's up to you which one's easier to read. Here, if you come back to this quite clearly reads as number of customers grouped by store, where the number of customers is more than 300. If we just left an asterisk there, then we'd have to remember that the customer table represents all the customers per store there. Okay, so let's go ahead and test your skills. In the next lecture, we'll give you some challenges with the having clause. I'll see you there. Welcome back, everyone, to this section on joins. So in this section of the course, we're going to discuss the various types of joins that are available to us with PostgreSQL. And really, a join at the heart of it just allows us to combine information from multiple tables. And let's take a quick peek at what we're going to learn in this section. We're going to start off this section by quickly discussing the as clause, which is a really useful clause for creating an alias. That is to say, it just allows you to rename a column whatever you want. Once you understand that, we'll move on to joins. So we're going to discuss different kinds of joins, such as inner joins, outer joins, full outer joins, unions, and more. So those are things also like left joins and right outer joins, etc. So lots of stuff to discuss here. We're going to start off with the simpler join types and then move on to the harder to understand or more complex join types. But overall, once you understand one type of join, the mental leaps required to understand the other types of joins isn't too bad. All right. So now that we understand what we're going to learn in this section, let's move on to the next lecture. I'll see you there. Welcome back, everyone, to this lecture on the as clause. Before we learn about joins, let's quickly cover this as clause or as statement, which allows us to create an alias for a column or result. And what we mean by alias is just an alternative name. Let's see the example syntax for this. This is actually quite simple. Instead of just selecting a column from a table, we say select column as, and then we decide on a new name to display in the data output. We can also use this on functions on a column. So we can say something like select column and then have that, instead of displaying as sum of that column in the data output, instead have it display as new name. Let's see some examples. So this is the way it classically works, where we say select customer ID from payment. And notice that the column name is the same in the data output below. We see customer underscore ID. Now let's see what happens if we were to use the as statement. So here we're saying select amount as rental price from payment. So notice here, instead of having the output reported as the amount column, instead we decided to give it an alias or rename it as rental underscore price. And maybe this will be easier for some other analysts to read when we actually show them our SQL query results. So really here, it's just for readability on the data output. And this starts to make sense, especially when we perform functions on a column. For example, select some amount as net revenue from payment. And instead of having the output just say sum of the amount, here we can clarify it with an alias as the total net revenue from the payment table. So essentially in net revenue, we've made around $61,312. Now keep in mind the as operator gets executed at the very end of a query. And this is where a lot of students, especially beginners, get confused. That means that we cannot use the alias inside of something like a where operator or a group by call. And I'm going to walk through an example of trying to do that and having it show an error, because a lot of students get confused on that particular notion. You essentially only get to use that alias in the select statement. Anywhere else, it's not actually going to be valid. So let's head over to pgadmin and walk through an example of that. Okay, here I am at my query editor. What I'm going to do is say select, and we're actually going to say count the amount from the payment column. So if I run this, notice I get back just count as my output. And if I just see this data output without any regards to the query, it's pretty unclear what this is actually counting. So maybe I want to clarify this using an alias. So I can say as, and counting the amount from the payment column is the same as asking how many transactions have occurred. So I can say number of transactions, run this, and now I see that the data output has been renamed to be num underscore transactions. And recall, with count, you can always just pass in anything here, such as an asterisk, and that will be the exact same thing. So here, saying count asterisk as num transactions from payment, using this alias, it makes it quite clear what the data output is actually showing us. Okay. Now let's imagine we were going to do a group by statement. So let's do the following. Let's say select the customer ID and then some amount from payments, and then I'm going to group by customer ID, essentially showing how much each customer actually has spent. So I run this and I get back the customer ID as well as some sum. However, if I'm looking at the data output, maybe it's not super clear that this sum happens to be their actual expenditure, because I don't see a dollar sign here anywhere. And unless I actually get to read this query and understand the thought process behind it, the data output results don't specifically tell me that this sum happens to be their total spent. So I can simply say as total spent, and notice I do this directly after whatever column or function result I want to rename. And then I run this, and I get back here in the data output total spent. Now, here is where I really want you to focus, because this is where beginners often make a mistake. Let's imagine that I wanted to clarify on the sum amount. We already know I can do something like this. Having some amount, and let's have it be greater than 100. And we actually did pretty much this exact same query, and I'm going to remove as total spent. So what am I doing here? I'm doing the exact same thing as before, except after I've done the group by and calculated the sum amount, I'm going to do an additional filtering using having, where sum amount is greater than 100. So I run this, and notice now my sums are all greater than 100. And now I'm going to use again my alias So just clarify that as total spent. So I run this, and now I get to see total spent here. Unfortunately, this alias gets assigned at the very end, which means I cannot do this. And this is where beginners try to do this a lot. They'll say having total spent greater than 100. And if they run this, you get back an error. It'll say column total spent does not exist, which at this stage is true. Total spent is only going to exist at the very end at the data output. So because an alias gets assigned at the very end, you cannot use it in something like a where statement or a having clause. Unfortunately, you have to go back and choose the original, either column name or the original function. So we'll have to say having some amount greater than 100, and we see back these results. So keep that in mind. These aliases get assigned at the very end, so you can't use them to filter by. So I'm going to show you another example of this. Let's just go ahead and remove group by and having some, and we'll just say amount. We run this. So here are all the customer IDs. Notice there's repeats as well as the amounts. Now let's imagine I wanted to qualify this for amounts greater than $2. Well, I could say from payment, then where amount is greater than 2. So I run this, and now notice I got rid of all those 199 transactions. Now, if I happen to use an alias on amounts, so we'll say as new name, I run this. Notice new name is now in the data output. Unfortunately, I cannot do this. I cannot say where new name is greater than 2. If I run this, I get the same error as before, that new name does not exist. So again, just to clarify, these aliases get assigned at the end, and unfortunately, you can't use them in the where clause or the having clause to filter by. Instead, just think of them as being used in the data output. And you'll have to use the original column name if you plan to do any filtering or comparison operations on it. All right, that's it for the as statement. As you can imagine, as we begin to join tables using join statements, it'll become quite useful to be able to assign aliases for clarification. Okay, coming up next, we'll begin discussing joins. I'll see you there. Welcome everyone to this lecture on the inner join. There are several types of joins, and in this lecture, we're going to go through what I think is the simplest join type, which is an inner join. And typically when students are learning about joins in SQL, they always start off with the inner join because it's the easiest to understand. First off, what actually is a join operation? Put simply, joins allow us to combine multiple tables together. Now, the main reason for the different join types is to decide how to deal with information only present in one of the joined tables. So let's begin by imagining a very simple example. Let's say our company is holding a conference for people in the movie rental industry. So before the conference actually starts, we're going to have people register online beforehand. And the registration is simply just providing their name, and we'll keep track of people as they register. And then the actual day of the conference, they're going to come in and log in through an iPad with their name. So after the conference, we end up having these tables. So we have a registrations table as well as a logins table. The respective ID columns indicate what order they registered or logged in on site. So we can see the registrations column. We have Andrew who registered first, then Bob, then Charlie, then David. And then we have logins with Xavier, Andrew, Yolanda, and Bob. For the sake of simplicity, we're going to assume that in this little small universe, all the first names are unique. So there are not 2 Andrews, there's not 2 Bobs. Every person has a unique name. And to help you keep track of the different joins, since we're going to be using these example tables throughout this section of the course, keep in mind that the registration names, first letters, go A, B, C, D. And if you take a look at logins, the 2 outstanding ones that are not in the registrations are Xavier and Yolanda, basically implying that they forgot to register but still showed up the day of the conference. So what does an inner join do? An inner join will result with the set of records that match in both tables. So the situation we have right now is in the registrations, we had Andrew, Bob, and Charlie, and David register for the conference. However, the actual day of the conference, when people were logging in, we only had Andrew and Bob show up that actually registered, and then Xavier and Yolanda, who forgot to register, they came in on site and then logged in. And keep in mind here that it looks like Charlie and David registered, but didn't end up showing up to the conference to log in. So we have that discrepancy there of Xavier and Yolanda in the logins table, and then Charlie and David in the registrations table. So where do we actually have a match in both tables? Well, we have Andrew and Bob. Andrew and Bob are the only ones that both registered and logged in the day of the conference. So an inner join is going to be able to join these tables together for records that are a match in both tables. So when we're talking about an inner join, we're only looking for the set of records that happen to be in both tables. And in this case, that would only be Andrew and Bob. So what's the actual syntax for this? Well, we can say select and then whatever columns you want. But in this case, we'll keep things simple by selecting all columns. And we say select all the columns from table A and then inner join with table B. And then we provide what we're actually matching on. So match on table A column is equal to table B dot column match. So what does that actually look like in practice? So if we color code this and think of the tables as Venn diagrams, and if you look up SQL joins on Google image search, you'll see a ton of Venn diagrams. So a lot of people like to think of it this way. If we see here that we're selecting from table A, inner joined on table B, where table A column match is equal to table B dot column match. So we're essentially saying grab table A and then grab table B, and because it's an inner join, only grab the rows that happen to be in both table A and table B. And we have to actually join these tables on a particular column, such as the name column that we saw in registrations and logins, because we know the names are unique over this small universe of people. There's only one Andrew, only one Bob, etc. Now, something to keep in mind, especially with an inner join, is notice that this Venn diagram essentially is only filled in the crossover middle. Essentially, stuff that can be found in both of these circles, table A and table B. Because of that, inner join is essentially symmetrical, which means if you select from table A and then inner join table B to look like this, select from table B, inner join on table A, you would get the same result. So getting from table A and then joining on table B is the same as getting from table B and then inner joining on table A. Keep in mind, this is only true for an inner join in this particular case. So switching around the orders here, even switching around the column match order, doesn't really matter for an inner join because it's the same regardless, because this is a symmetrical Venn diagram. So let's actually work through this and what would actually happen in a more realistic situation with the example tables. Here, we're going to say select all the columns from registrations, inner join logins. So it's essentially saying take registrations table and then perform an inner join with logins, seeing the rows that happen to be in both registrations and logins. And then we have to decide what column we're actually looking at in order to perform this inner join. In this case, we'll do it on the name. We'll say on registrations dot name. So it's the table name dot and then the column name is equal to the table name dot column name. So logins dot name. And keep in mind, you could swap any of these orders around because it's an inner join, it's symmetrical. It doesn't really matter if we're saying select from registrations, inner join on logins, or select from logins, inner join on registrations. And you can also swap around that on equals sign to be something like on logins.name equals registrations name. Okay, so here we're just generally showing the syntax. And we're looking at that name column. So then we look at, well, where do we have a match in both tables? And that happens to be Andrew and Bob. And so we said select all the columns from these. So that includes the registration ID column as well as the login ID column. So we have these 4 columns, we have the matches, and we join them together to see this result. So this is selecting all the columns from the resulting of registration inner joined with logins on the name column. Okay, and that's it. That's an inner join. Again, an inner join is looking for matches that exist within both tables. And here we're saying select all the columns. Notice, because we said select all the columns, the name column happens to be duplicated or repeated twice because there's both a name in the registrations and a name in the logins. If you wanted to get rid of this duplication, what you can do is actually specify what columns you want. So here I'm saying select registration ID, logins.name, then login ID from registrations, inner join logins on registrations.name equals logins.name. So you might be wondering, why do I have to specify logins.name instead of just saying name? Well, the reason for that is because name existed in both tables. So we had both tables share a column name, which means if I'm selecting something after a join, I should specify what table I'm referring to in regards to the name column. And in this case, it doesn't really matter. I could have said registrations.name or logins.name, but I should be specifying because there's a duplicate name column in my SQL query. I should be specifying what actual column I'm looking at. Because recall, here we had both the name column from registrations and the name column from logins. So if I only want one of those, because it's duplicated, I'll specify that I'm looking at logins.name column. Remember, again, that table order won't matter in an inner join. And also, if you see just join without the inner, PostgreSQL will treat it as an inner join. Now, I'd highly recommend that you always type out the full inner join, but some people, as they get really used to PostgreSQL, just use the shorthand of join, which defaults to inner join. Okay, let's go ahead and jump to pgadmin and work through a couple of examples. Okay, here we are in pgadmin. Now, if we come over here to schemas under public, under tables, we can see the various columns that are in the tables. So if we take a look at, for example, the customer table, we can expand the columns and we can see we have the customer ID and then the associated information with that, such as store ID, first name, last name, email, etc. And we can see in the payment table, we have the payments as well as a specific payment ID and then the customer ID. So what I want to begin exploring is if there was a way I could join the payment table with the customer table in order to get maybe the customer email associated with a specific payment. So for example, I can say, select everything from payments. We'll go ahead and run that. Let's put this on 2 lines together just for readability. So I run this and I can see I have a payment ID and then a customer ID, staff ID, rental ID, amount, etc. Let's go ahead and do the following. We'll say, select everything from payment, and we'll perform an inner join with the customer table. So this is essentially table A inner joined with table B. And since I'm doing an inner join, I'm only going to get back results where that particular customer happens to be both in the payment table and in the customer table. And now I have to decide what I'm actually going to join them on. So I have to join them on a column that is associated with both the payment table and the customer table. And I can see I have this customer ID column, which essentially uniquely identifies every single customer. So let's go ahead and join it on, and then we'll say payment dot customer underscore ID equal to the customer table dot customer ID. And if we run this, we should get back a lot of columns. So we run this and we can expand on this. And now you'll see I have the payment ID, customer ID, essentially all the information from the original payment table. But if I keep going further, now I see the repeated information based off customer ID, but now it's on the customer table. So I see the store ID, first name, last name, email, address, etc. All right, now let's see how we can select certain columns from each table. If I'm referring to a column that can only be found in one of the tables, then I don't need to specify what table it should come from. Luckily, PostgreSQL is smart enough to understand that if I refer to something such as select the payment ID column, since that's only found in the payment table, I don't need to actually clarify what table it should come from. However, if I'm referring to something like customer underscore ID, that can be found in both tables. So I should clarify what table I'm actually asking the customer ID from. And since I'm asking for payment ID, I should probably link it to the customer ID from the payment table. So I do this by saying payment dot, and then I ask for the customer ID. And then finally, let's go ahead and choose some column that is unique to the customer table. For example, their first name. So we'll simply say something like first underscore name. And let's go ahead and try that out. I'll put this from on a new line here. So I'm selecting the payment ID, which is unique to the payment table. Payment.customer ID. Customer ID is not unique to either table. So I clarify what table I'm actually referring to for that column. And then we select first name. First name was unique to the customer table, so I don't need to say customer.firstname. Optionally, you can say customer dot first name, and nothing will happen or nothing will change, but it's just easier to say just first name. So let's go ahead and run this and see the results. Notice now I get to see payment ID, customer ID, and first name. So this is the general syntax that we're using for inner join. Notice how the inner join is only going to join customers that are found in both payment and the customer table. Essentially what that means is by providing this inner join, I'm not going to see customers that have never created any sort of payment because I'm only looking for customer IDs that are found in both the payment table and the customer table because of this inner join. So again, general syntax, I select columns from a table, let's say table A, inner join on table B, and then on payment.customer ID equal to customer.customer ID. So table A, the identifying column equal to table B and the same identifying column. Keep in mind, this column could be called something else in the customer table. It could be maybe shortened to just C underscore ID. That as long as they're referring to the same thing, the customer ID, that's okay. Typically, in a well-designed database, these should have the same column name, but keep in mind sometimes the column name will be slightly different in one table than the other. So it's up to you as the SQL query developer to just make sure and double check that it's referring to the same thing. And as I mentioned before, for an inner join, technically these orders don't really matter. I could say from customer, inner join with payment. And if I run this, I actually get back the exact same results. And depending on what version of SQL you're running or PostgreSQL, they may be in a slightly different order. However, keep in mind those results should be exactly the same because we're only looking at the intersection of that Venn diagram, stuff that's both in table A and table B. So it doesn't really matter what order you're looking at it because that Venn diagram is symmetrical. Okay, that's it for the inner join. Again, this is pretty much the simplest join possible, just looking at rows that happen to be in both tables. Thanks, and I'll see you at the next lecture. Welcome everyone to this series of lectures on outer joins. So as I mentioned, there's a few different types of joins, and one of the subsets of these types of joins are outer joins. And there's actually a few different types of outer joins. Outer joins essentially allow us to specify how to deal with values only present in one of the tables being joined. And these are more complex joins than the simpler inner join, which is essentially the default join, where you only grab rows present in both tables. So definitely take your time when trying to understand these outer joins, especially when we start talking about left and right outer joins. So in this series of lectures, we're going to start by talking about full outer joins, which is the simplest outer join. And then we'll go into a lot of detail about the left outer join, which is probably the hardest for beginners to grasp. Once you understand that, we'll just quickly go over right outer join, since it's essentially the reverse of a left outer join. And if you understand a left outer join, you pretty much already understand a right outer join. It's just the opposite. But let's not get too carried away. Let's begin with the full outer join. So let's start with the full outer join. Now let's review the two example tables from the previous lecture series on inner joins. Recall we have these registrations tables and this logins table where we have people registering for a conference, and then depending on whether or not they showed up or if they registered, we have them log in on site. Here we have Andrew, Bob, Charlie, and David, or A, B, C, D. They registered. Logins, Andrew and Bob show up. They're present in both tables. However, we have Xavier and Yolanda. They forgot to register, but they still showed up and logged in anyways. Okay, so we know we would join these tables together on the name column. Again, in this little universe, we're going to assume that the name is a unique identifier. There's no such thing as two Andrews or two Bobs in the world. And recall, using that inner join that we learned about previously, we could match Andrew and Bob in both tables. However, keep in mind we have names that only appear in one table, and that is Charlie and David in registrations and Xavier and Yolanda in logins. So let's see how the different outer joins deal with this particular discrepancy. We're first going to take a look at the simplest, which is a full outer join. And this actually might be even easier to understand than an inner join. So an outer join, or a full outer join, just grabs everything. So the syntax is select all the columns from table A, do a full outer join of table B, and then on wherever that column match occurs from table A equal to table B dot column match. And it's essentially just grab everything, whether it's present in both tables or present in only one table. Notice that it doesn't really matter again if table B and table A order is switched here because this is completely symmetrical. So because this Venn diagram is symmetrical, you can switch off the table order because you're going to grab everything anyways. So let's take a look at this. The actual syntax here would be select all the columns from registrations, perform a full outer join on logins on registrations.name equal to logins.name. So let's actually see how SQL thinks about this in the background. First, we're saying grab everything from the registrations table. So I'm going to have to first make this just font-wise a little smaller so we can fit in the results table. And we're going to fill in the results table the way we can think about this. We're saying grab everything from registrations and a full outer join on logins. So we fill in first everything from registrations. Again, we don't really need to worry whether or not they're in table B or table logins because we're grabbing everything anyways. So we fill in with Andrew, Bob, Charlie, and David. And then we're doing a full outer join on logins. So we need to start filling information for where we actually have a name match. And we know we have a name match on Andrew and Bob. And then we fill it in with the corresponding login ID. In this case, it was number 2 and number 4. Now the issue we arise with is that we didn't have a Charlie or David in logins, but we're still asking for everything. So what SQL ends up automatically doing for us is filling this in with null, essentially clarifying to you that there was no value there present. So there was no Charlie or David in the logins column. And since this is a full outer join on logins, we also need to fill in the rest of logins, which was Xavier and Yolanda, and then the corresponding null values for the registrations table because they were only present in the logins table. So this is what it would look like to do a full outer join on these two tables on the name column. We grab everything and then fill in for null values where we only had a row present in one particular table. So this is the easiest outer join to understand because you're essentially just grabbing everything. Now the next thing I want to quickly discuss is qualifying a full outer join with a where statement. And we can do this in order to get rows unique to either table. In other words, rows that are not found in both tables. Essentially, this is the exact opposite of an inner join. Let me show you why. The way this works is we say the following. We'll say select everything from table A with a full outer join on table B on table A.column match is equal to table B.column match. That's what we had last time, and that filled in the entire Venn diagram, including the intersection. However, we're going to add in a where statement to qualify a little further. And this is going to add in the statement where table A.id column is null or table B.id column is null. So that essentially means that we're looking for the actual values where one of the table's ID columns is null or the other table's ID column is null. Essentially the opposite of an inner join because this will only grab things that are unique either completely to table A or unique to table B. Keep in mind, notice here I could have switched the order from table A to table B because this is again symmetrical right down the middle. So what does this actually look like in our example? We'll say something like select everything from registrations, a full outer join on logins, on registrations.name equal to logins.name, and then we can specify where this registration ID is null or where logins.login ID is null. So this to show you how this would actually work. This is what we had last time. This is a full outer join. And notice here we have null values for our registration ID and null values for our log ID. Technically, we could have done the checking of null name as well, but we're just going to use the ID column here. And what we're going to do here is we'll specify, grab them where there's only null values for that. So look here, we're going to add in where registrations.regid is null or where logins.logid is null. Essentially, you can think of this as adding in a where statement after you've already done the join. So you're just further filtering. You're going from this full outer join table and then specifying, find me where those ID columns are null. And that essentially removes those first two rows, which was the match for Andrew and Bob. And now this is going to show us the results that are unique to only table A or only table B. We no longer have rows that can be found in both tables. Essentially, the exact opposite of an inner join. So let's see a quick example in pgadmin of full outer joins, as well as adding in that qualifier. Okay, here we are at pgadmin. Let's imagine that some new privacy rules have been implemented, and we want to make sure that we don't have any payment information that's not attached to customer, or that we don't have some customer information that isn't attached to any payments. Essentially, we want to make sure that all the payments we have is associated with a current customer, and all the customers we have are associated with some historical payment. We don't want to have some customer ID information for someone that's actually never purchased anything in any of our rental stores. So that's the new privacy update. We're just kind of imagining the situation. So what are we actually going to do here? We can say select everything from payment just to get an idea of what we're working with. We have, again, this payment ID and this customer ID. And I want to make sure that essentially all the payments here are associated with a current customer. And if I select everything from customer, that these unique customers are associated with some sort of payment. I don't want to have any customer here that hasn't actually made a historical payment. So the way I'm going to do that is I'll say select everything from customer and do a full outer join with payment. And just as before, we're going to say on. We'll say customer dot customer ID equal to payment dot customer ID. So because this is a full outer join, that's just going to take everything and join it together. So essentially, this is every single row found in every single table. So again, it's everything from customer and everything from payment. But recall the new privacy idea that we wanted to implement was to figure out, make sure we don't have any information that's essentially unique to payment, not associated with customer, or unique to customer, or we for some reason have customer information like their email when they've never done a historical payment. So that means I want to perform an additional filter with a where statement. So I want to check where on my customer table that customer ID happens to be null. So we'll say where customer ID is null. We can put that in lowercase. Or where payment ID is null. All lowercase there. So what is this actually saying? It means we're going to fully join the customer table and the payment table where those customer IDs join up. And now I'm going to filter it to attempt to find rows that are either only unique to the customer table, meaning we have information about a customer that's never made a payment, or only unique to the payment table. Notice here how I'm using the payment ID, which is a unique identifier for the payment table. If we keep going over, we can see here every single payment has this unique payment ID. And if I run this, notice I get back empty results, which actually means we're in compliance with this new privacy policy. We don't have any payment information not associated with some customer, and we also, more importantly, don't have any customer's email information, their first name or last name, who has never made a payment. Now, what's another way we could confirm this? Well, I could confirm this by taking a look at the distinct customer IDs in both my customer table and my payment table. So this alone basically tells us that there are no rows that are completely unique. Essentially, there are no customer IDs that are completely unique only to the customer table or only to the payment table. If we have information on a customer, it's because they've done some payment in the past. And we're able to select this with a full outer join and then filtering to make sure that there wasn't anything unique only to one of those tables. And to confirm this, just so we can wrap our head around this idea, let's go ahead and just count the distinct customer IDs from the payment table. So if I run this, there's 599 unique customer IDs or distinct customer IDs in my payment table. And if I take a look at my customer table, refresh this, there is also 599 distinct customer IDs. Now, technically, this doesn't fully answer the previous privacy compliance policy because there could possibly be different ID numbers in different tables. The real way to answer the previous question to make sure there wasn't any customer information that didn't have payment information was using that full outer join and then filtering an additional where with the null statements on those unique identifiers for the customer ID and payment ID. This technically by itself only further validates that last query we did, but doesn't actually fully answer the question. Because technically there could have been maybe customer IDs that were letters in one table that were 599 unique letters or a series of letters. And then the other table could have 599 unique numbers. So keep that in mind. While this does clarify and verify what we did, it doesn't 100% confirm that privacy policy. The only way to do that was using that full outer join with the additional where that we just saw. So we're learning about really powerful tools here. And so far we wouldn't have been able to answer those sort of questions without learning about the different join capabilities. Okay. So coming up next, we're going to learn about a left outer join, which is typically the join that usually trips up beginners, but we're going to take it slow. And once you really get the hang of it, especially with those Venn diagrams, it shouldn't be too bad. Thanks, and I'll see you at the next lecture. Welcome everyone to this lecture on the left outer join, otherwise known simply as just a left join. A left outer join results in the set of records that are in the left table. If there's no match with the right table, then those results are null. Later on, we will learn how to add where statements to further modify a left outer join. So, what does a left outer join actually look like? Here, notice that our Venn diagram is no longer symmetrical, which means the order will actually matter. Here we're saying select everything from table A and do a left outer join on table B. The left-hand table is the first table we're referred to in that from statement. So that's why table A there is seen on the left. So we're saying select everything from table A left outer join on table B. On table A.columnMatch is equal to table B.columnMatch. So notice we're essentially just grabbing information from table A where there's either exclusive to table A or table A has a match with something in table B. If something is only found in table B, then it is not going to be returned in the query. And again, recall that a left outer join can be shortened to just left join in SQL syntax. So it doesn't matter if you use left join or left outer join. Now, because of this asymmetry, this is where beginning students often get confused. Previously, everything we saw, it was symmetrical in that Venn diagram, which means the table order didn't matter. When it comes to a left outer join or a left join, the order does matter because we have to actually specify what the left table is going to be. So notice here we're saying table A, which means we're going to grab things that are exclusive to table A or can be found in both table A and table B. We are not going to be returning anything exclusive to table B. So again, not returning anything exclusive to table B. So let's explore a left outer join with our two example tables. Here we have registrations and logins. So what we're going to say here is say select everything from registrations, perform a left outer join on logins on registrations.name equal to logins.name. And what does this actually look like? Well, it's going to return the following. Recall that we're going to grab everything from the registrations table, and if there happens to be a match with the logins table, we'll go ahead and return it. If there is no match, we're still going to grab that information from the left-hand table, which is from registrations, but because there's nothing in table B for it, we're going to fill it in with null. Notice that things that were exclusive to the right-hand table, that is the logins table or table B, that was Xavier and Yolanda, we don't actually see them in this result of the left outer join. Previously, when we saw a full outer join, we did see those results. But now, because we're specifying a left outer join, we only see things based on that left-hand registrations table. It either belongs to both tables or only to registrations. If it only belonged to logins, we don't see it returned here. So again, everything from registrations ends up showing up in this left outer join, which is why it's critical to remember that table order does matter in the SQL query syntax when it comes to a left outer join or a left join. Now we can further qualify this with a where statement to get rows unique only to the left table. So, for instance, what if we only wanted entries unique to table A? Those are rows found in table A and not found in table B. So we're essentially just grabbing rows unique to table A, not found in this other table. So the way we do that is by saying the following. We're going to again select from table A, do a left outer join on table B, specify the column to match on, and then we're going to say where table B is null. Because if table B is null, that means the resulting rows would only be unique to table A. So, recall this was our previous query. This is just the left outer join, registrations and logins. And what we're going to do here is if we take a look at the login ID column, we notice we have those null values. So what we're going to say here is go ahead and grab where logins.logid is null. And because the logins ID, that is from the right-hand table or table B, was null, this answers the question that these particular rows are exclusive to the left-hand table or the registrations table. So Charlie and David can only be found in the registrations table. They cannot be found in the logins table. So this is a left outer join with an additional specification to only grab tables unique to the left-hand table, that is table A or registrations in this example. So definitely take your time with these and feel free to watch this video a couple more times. Sometimes it takes students just a couple of times of watching this video to truly get the understanding of a left outer join. This is the most complicated join because it is a non-symmetrical join. So let's see some examples of a left outer join in PG Admin. If this is still a little fuzzy to you, I would highly recommend that you go back, watch this from the beginning, just let things cement theoretically, and then come with us and join some SQL queries in PG Admin. Okay, I'm going to hop over to PG Admin now. All right, the two tables we're going to be exploring for this particular example is the film table, which I can just select everything first from the film table so we can get an idea of what's in it. So I run this. We have a film ID, which is a unique identifier per film, the film's title, a description, release year, language ID, rental duration, etc. So we have that information here, basically information about the film. The other table we'll be taking a look at is the inventory table. So the inventory table, if we run this, it basically has a unique inventory ID, and then the film ID, which matches up with the film table, and then the store ID. So essentially this says that we have film ID 1 located in store ID 1. And then we have another repeat, essentially a duplicate copy of film ID 1, also in store ID 1. So this essentially begins to imply that we have multiple copies of films in certain stores, and we also have the possibility of films only being located in one of our two stores. So let's start exploring this. Keep in mind, each row in the film table may have 0 or many rows in the inventory table. So for example, we have film ID 1 is currently in inventory both in store ID 1 and store ID 2. So we have lots of copies of film ID 1 in both stores. So what I'm going to do is the following. We'll say select film.filmID, film.title, and then inventory ID. So the reason I don't need to specify inventory ID of a table is because it's unique to the inventory table. However, film ID can be found in the film table. And in fact, title is actually unique to the film table, so I don't need to mention that as a table as well. So we have select film ID, title, and inventory ID. And this is where we're going to do our join. We'll say select from film, left, and you can say either left outer join or just left join. Those are syntax-wise the same thing. And we're going to say inventory on inventory.film ID equal to film.film ID. We run this, and note what we're having here. It's basically telling us the film ID, the title that belongs to that film, and then its specific inventory ID. And if I wanted to, I could expand on this by asking for also the store ID. I could run this again, and I can see we have Academy Dinosaur, multiple copies in store 1. as well as multiple copies in store 2. So that is a left join, essentially showing us the left joining of film on inventory. So what does that actually mean? Because film is on the left-hand side, I'm only going to see rows that are either in just the film table or in both film and inventory. Right now, I am not seeing any films where they happen to only be in inventory for some reason, but not have some sort of title attached. So because some rows in the film table do not have corresponding rows in the inventory table, we would see that the values of the inventory ID are null. So there's lots of rows here, but eventually as you scroll down, you may find something to be null. So what I'm going to do here is show you that. We're going to say where the inventory dot film ID. Note here how I have to specify the table for film ID because it is found in both tables. And I'm going to say is null. I'm going to run that. And often you also see null be in all caps. So keep in mind, you can also just do all caps null. Run that, and it looks the same. It's up to you whichever manner you prefer. But what is this actually showing us? This is showing us a film ID, a unique identifier for the film, as well as the title. And it's showing you that we don't have this in inventory, which means essentially if someone comes up to us and they ask, hi, where or what store can I find Alice Fantasia in? We can do this query, and it basically answers it that we don't actually have Alice Fantasia in our inventory. In fact, we don't have any of these movies currently either in our inventory or in any store. We have information on them. I can tell you the release date or the actors in them, etc. from the film table, maybe doing other joins. But unfortunately right now, we don't have them in inventory. And so here you can begin to see the use case for a left outer join, essentially showing us films that we have information about, but that are not in our inventory because we're specifically checking where that inventory film ID is null. Okay, so that's it for this lecture on the left join. Keep in mind, we're going to get more practice on this with your challenge questions, so feel free to review this lecture as many times as necessary. Thanks, and I'll see you at the next lecture. Welcome everyone to this lecture on right joins. A right join is essentially the exact same thing as a left join or left outer join, except that the tables are switched. And often, beginners get confused when first starting to learn SQL, especially when they hit that left outer join, which is the most difficult join to learn about because it's asymmetrical. And then suddenly, they're introduced to this concept of a right join. And students often get confused because it seems like the right join is a completely different thing. But the reason I don't want to dwell on it too much is because a right join is essentially the exact same thing as a left join, except you just switch the tables around. So this would be the exact same thing as switching the table order in a left outer join. And in fact, you can pretty much go on just using a left join for two tables and just switching up the order of the tables in order to satisfy whatever needs you have. So it really depends on how you think about the tables and what order they come in your mind, whether table A is on the left, table B is on the right, or if table B is on the left and table A is on the right. So I want to quickly show you some examples through a Venn diagram. So a right outer join, notice this looks a lot like a left outer join, except it's just flipped along the axes. So we're saying select everything from table A right outer join on table B, where table A has a column match equal to table B. So what this is saying is essentially the exact reverse of a left join. And what this is saying is return back rows that can be found either exclusively in table B or in both table B and table A. And do not return back rows that are exclusively only found in table A. Notice how this would have been the exact same thing as a left join had we just switched around the table order. Okay, so again, this is pretty much the exact same thing as a left join, except you're switching those tables around. And you can actually get back these same results by doing a left join and selecting first from table B with a left join on table A. So keep in mind, really the right outer join is just to help you keep the same tables in the same order in your mind of table A's on the left and table B's on the right, but switching up the results you get. And keep in mind, you can do either right outer join or right join. They both work fine. And just like we could with a left outer join, you can also add a clarifying where statement to say something like where table A.id is null in order to clarify that you only want tables that can be found exclusively in table B and are not found in table A. Okay. So it's really up to you and how you have the tables organized, quote unquote, in your mind when it comes to choosing a left versus a right join. Since depending on the table order you specify in the join, you could perform duplicate joins with either method. So if two tables can be joined and you can get results with a left outer join, you should also be able to get the exact same results with a right outer join or right join by switching the table order and playing around with that table ordering or playing around with any table ordering in the where results, depending on the exact query you're doing. So really take your time to understand the left outer join extremely well. And then if you want, you can begin to use the right join if the moment calls for it. Or if you want, you can always just stick to left join and switch around the table order there. Okay. So again, hopefully if you understand left outer join well enough, you can see how right outer join is really the brother or sister of left join. You're just kind of flipping that and just keeping the table order the same in the query itself, but flipping the results around. And if you wanted to, you could just flip the tables in the query in order to keep the left join call and not have to switch to a right join call. So take your time with these two slides. This pretty much just answers the question of what a right join is. And if these slides are confusing to you, then you need to go back and really take your time to review the left join and left outer join. Because once you understand that really well, then these two slides should be very clear in the fact that it's just a left join with the tables flipped. Okay. Thanks, and I will see you at the next lecture. Welcome back, everyone, to this lecture on unions. The union operator is used to combine the result set of two or more select statements. The way I like to think about a union versus the joins we've already learned is that it basically just serves to directly concatenate two results together, essentially just pasting the results of two select statements right on top of each other. The syntax is simply the following. You have your first select statement, and then you have a union with another select statement. Something to keep in mind is that these should be logical and they should match up in a way that you can stack the results right on top of another. Let's go through a simple example. So let's imagine we have these two example tables, and what we're doing is we're organizing the sales per year per quarter. So I have one table with my first quarter sales for the year 2021, where David sold 100 amount and Claire sold 50. Then I have another table storing my results from the second quarter. Again, David now has sold 200 and Claire has now sold 100. If I actually want to put together the information from these two tables in order to get kind of total results or see every single time a amount was sold for the first half of the year, I can't really use the typical joins that we're already familiar with. Instead, what I should be doing is just pasting one of these on top of the other. And this is perfect for a union. So all we need to do is say, select everything from the first sales quarter, union with select everything from the second sales quarter. And what it's going to do is just grab the results from the first query and then paste them right on top of the second query. And as you can imagine, if you wanted to, you could have multiple union calls just pasting together these different results. And what you can also do is, for example, if you want it to be ordered or sorted by the name, you can just add an order by call after this to order it by the name. Thanks, and I'll see you at the next lecture. Welcome back, everyone, to this section on advanced SQL topics. Basically, this section consists of topics that didn't really fit in well with the flow from the previous sections because they don't actually need to be learned in any particular order. So what we're going to be talking about, one will be the subquery, basically a query within a query, and we'll also talk about a self-join. Let's go ahead and get started. I'll see you at the next lecture. Welcome everyone to this lecture on the subquery. In this lecture, we're going to be discussing how to perform a subquery as well as how to use the it's this function in conjunction of a subquery. A subquery allows you to construct more complex queries, essentially performing a query on the results of another query or using the results of another query. The syntax is relatively straightforward and involves the use of two select statements. Let's imagine some hypothetical table that consists of the student names and their resulting test scores. So it's a very simple table of just 2 columns, which means a standard query on this table, if you wanted to grab everything, would look like the following. We say select the student column, comma, grade column from test scores. And this will return back 2 columns, the student's name, such as Jose, and then their grade, let's say 95%. Let's imagine you wanted to grab the average grade across the entire class. Then you would just say select average grade from test scores. So we already know how to grab all the information from the table, as well as the average score or average grade from all the students. Now let's imagine you wanted to answer this question. How can we get a list of students who scored better than the average grade? Given what we already know so far, it looks like we need to actually do this in 2 steps. First, we would have to get the average grade and then write that down somewhere and then compare that to the rest of the table against it to filter out the students. This is where we can actually use a subquery. So this is where a subquery can help us get the results in a quote-unquote single query request. Essentially, just needing to type out everything one time. So the way we would do this is the following. We would say select student grade from test scores where grade is greater than, and here in parentheses, we have our subquery, where we're going to have select average grade from test scores. So notice what we're doing here. We're first going to run the code that's inside the parentheses, the subquery, and that's going to return back the average grade across the table. Then we're going to be able to use that result in order to select students who have grades greater than the average. So recall that inside the parentheses, since this is going to be run first, this is going to yield some sort of result, such as 70. And then, once that subquery is done and returns its results, SQL is then going to run this other query outside of the subquery. So, you'll end up getting a list of students and their grades where they happen to be above 70 or wherever the average happens to be. So this allows us to simply type this out instead of having to do 2 separate queries, writing the results out of one and then using it in another. And this is now going to be flexible to any changes within the table. The subquery is performed first since it's inside the parentheses. Keep in mind we can also use the in operator in conjunction with a subquery to check against multiple results returned. For example, let's imagine we wanted a subquery that operated using a separate table. So we wanted to grab the students and grades from the test scores table where the student happened to be present inside another table. So we could do this with a join, possibly, but the other way we could do it is with a subquery. So we could, in our subquery, say, select the student name from the honor roll table, and then that will yield back some results of the student names. For example, let's say Zach, Chris, and Carissa are the students in the honor roll. And then, after that subquery is done executing, we can say, select the student and their grade from test scores, where a student is in this list of students. So note here, this seems to follow along very similar to a join, but sometimes, especially for complex queries, it's easier to think of them as a subquery. Now, the exists operator is used to test for the existence of rows in a subquery. Typically, a subquery is passed in the exists function to check whether or not any rows are returned with the subquery. So typical syntax would look like this. We say select some column name from some table name where exists and then the actual subquery. So select column name from table name where we have some sort of condition. And then that's going to return true or false depending on whether or not there were any rows returned. So subqueries and exists are really best learned through example. So let's go ahead and jump to pgadmin and work through some examples of using a subquery as well as the exists function within pgadmin. Okay, here I am inside pgadmin. Let's go ahead and work through an example similar to what we saw in the slides of a subquery. So to do this, I'm going to first select everything from the film table so we can remind ourselves what the format is. It looks like the film table has film ID, title, description, etc. And it also has a rental rate. Let's go ahead and calculate or return back the films that have a rental rate that is higher than the average rental rate for all the films, similar to the test score example. So the way we do that is we start off by, depending on how you want to work this from the inside out for the outside in, let's go ahead and start with the subquery. So the subquery should be first calculating that average rental rate. So the average rental rate of all the films, if we expand on this, we can go ahead and see it's $2.98. So this is going to be our subquery. Instead of having to use the scratch pad and write down this number, let's go ahead and have this be more dynamic. Wrap this in parentheses, so now it's a subquery. And then what we're going to do is say select. Let's go ahead and select the title column and the rental rate column from the film table where, and here we're going to say rental rate is greater than, and it's going to be greater than the results of this subquery, which is $2.98, which means when I run this, I should see back all the rental rates here, $4.99, $2.99, etc. These are all greater than $2.98. Okay, so notice here that the subquery in parentheses will get executed first in order to calculate that average, and then it becomes part of this larger query. The other thing that's important to notice is this particular subquery returns back just a single value, the average rental rate, which means it's okay to use a comparison operator against it, such as is equal to, is greater than, is less than. If your subquery, however, returns back multiple values, then you need to use the in operator on it. So let's work through a more complex example where we're going to actually use a join along with a subquery. So subqueries can actually have a join in it. So first, let's explore a couple of tables that we haven't seen in a while, so I just want to make sure we remember them. I'm going to select everything from the rental table. So if we run this and expand this back out again, we have a rental ID, a rental date, inventory ID, customer ID, and then we have a return date, which is what we're going to be focusing on, and then a staff ID and a lab or last update. We also have inventory. So let's check our inventory table. Run that. This has an inventory ID, film ID, store ID, and then a last update there. So let's imagine we have a situation where I want to actually grab the film titles that have been returned between a certain set of dates. So if we go back to select everything from rental, we have this rental date. Let's go ahead and grab all the films that have been returned between, let's say, May 29th of 2005 and May 30th of 2005. So that would be select, in this case, everything from rental. And then we're going to do here is say where this return date, if we come back here, we have this return date is between 2005 and let's say May 29th and 2005 May 30th. So we run this, and now everything here has been returned basically on May 29th. Okay. So notice here that in the actual rental table, I do not have the film ID. So if I want the film ID, I'm going to need to join this rental table with inventory, which actually connects the inventory ID. Because notice here I have an inventory ID, so I can use that in conjunction with the inventory table to then grab the film ID. So I have a specialized primary key for each rental, and then I have the inventory ID. So I'm going to use that. So let's say instead of selecting everything from rental, we're going to say select inventory dot film ID from rental, and let's perform a join on this. So we'll say in our join on inventory dot inventory ID equal to rental dot inventory. Make sure we spell this right. Inventory underscore ID. Now let me zoom out just a tad so we can see this whole thing. So what I'm doing here is I'm going to grab the film ID from the inventory table because it's not available to me on the rental table. And then I can use the inventory ID column that happens to be in both inventory and rental table in order to join these together. And then I'm filtering based off the return date. And if you want, you can specify the return date being part of the rental table, but it's only found in the rental table. So you can either do where rental.return date or just return date because it's exclusive to just one of the tables. So you don't need to specify what actual table we're looking at. So let's go ahead and run this. And now I get back this list of film IDs. So this is a list of all the film IDs that happen to be returned between these two dates. Now let's imagine I wanted the title of these. Well, what I could do is I could use this as my subquery, and now I have this list of results, which means I can use the in operator. Again, note the subquery is returning back multiple results, so I can use the in operator. And now I could just say select film ID, comma title from film, where the film ID is in, and then we have this list of film IDs. So I run this, and now I get back the film ID as well as the title. Keep in mind, PostgreSQL is going to operate this as efficiently as possible, so the order is not going to be maintained. If you do want to do some sort of ordering, you would do that at the very end after this last parentheses, because technically this subquery happens first. It gives you back that list. Then you organize everything here, and then at the very bottom on the last line, make sure it's outside the parentheses of the subquery. You can say order by something like title, and it will order by title. Or alternatively, you can order by the film ID. Okay, so that is a subquery using the in operator because the subquery returns back multiple results. And finally, let's walk through an example of using the exists operator. Let's imagine we wanted to find customers who have at least one payment whose amount is greater than 11. And we actually want to grab the first name and last name of those customers. The way we can do this using the exists operator is the following. We'll say select the first name and last name from the customer table, and we'll go ahead and say customer as C, where, and this is where we're going to use the exists operator. So recall that the exists operator basically just checks to see if rows exist in the actual return subquery. So that means we're going to do this. We're going to say exists, and in the subquery, we'll say select. We'll just go ahead and select everything from, and we'll say payment as P, where, just put this on multiple lines. It's a bit easier to read. We'll say where P dot customer ID is equal to C, which is the original customer table, dot customer ID, and amount is greater than 11. So note what we're doing here. We're going to say select the first name and last name from the customer table, where, and then the exists operator is checking to see if any rows are returned based off this subquery. Or we're saying select everything from the payment table where the payment customer ID matches the customer ID and the amount they paid, which comes from the payment table. If you want, you could say p.amount, but amount is exclusive to the payment table, so we don't need to clarify further, is greater than 11. So if we run this, we get back the names of, in this case, if I expand on this, these 8 people. So these are the first and last names of people who happen to have at least one payment whose amount is greater than $11. So in this example, what's happening is for each customer in the customer table, the subquery checks the payment table to find if that customer made at least one payment. So if that particular customer made at least one payment using this matching criteria and that the amount is greater than 11. If you wanted to do the opposite of this, essentially check for customers that have not made any payment greater than $11, you could add a not operator in front of exists there. Run this, and then you would get back basically any customer that did not happen to be one of those 8 customers. Okay, that's it, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on self-join. A self-join is a query in which a table is joined to itself. Self-joins are useful for comparing values in a column of rows within the same table. So the reason we talk about this as advanced SQL commands instead of in the join section is because this sort of use case is more dependent on your table structure and the actual question you're trying to solve. So it's not as common as just a normal inner join, for example. So let's discuss self-join in a little more detail. The self-join can really be viewed as just a join of two copies of the same table. Keep in mind the table is not actually copied internally, but SQL performs the command as though it were. And the other thing to keep in mind is there's no special keyword for a self-join. It looks just the same as a simple standard join, and it carries the same syntax with the same table happening to be in both parts. However, when you are using a self-join, because you're using the same table, it is necessary to use an alias for the table. Otherwise, the table names would be ambiguous within the self-join. So let's see a syntax example of this in order to see what I'm talking about when I mean the same tables being joined as well as those table aliases. So here we can see the syntax for a self-join. I'm saying select table A.column, comma, table B.column from table as table A, join table as table B on table A dot some column matching to table B dot some other column. So what's actually happening here? Well, the main thing to focus on are these table names. Notice in green here, we're saying from table as table A, join table as table B, which is me assigning two different aliases to the same table. This is what allows me to perform the self-join. The main thing to keep in mind is that even though you see representations of table A, table B, and just table here, all of these are actually referring to the same table. We're just using the aliases in order to organize this. Okay, so I think this is best explained through an example. So I want to show you a more realistic situation of when you would want to actually use this. Let's imagine that we have a company and we have some employees in this company. And employees have to send reports to other employees. So I have this table of employees with their primary key, employee ID, which is just a unique identifier per employee, then the name of that particular employee, and then the ID of the person they need to send a report to. So each employee sends reports to another employee. For example, here I can see that Andrew, employee number 1, sends a report to employee ID number 3, which happens to be Charlie. So Andrew's sending reports to Charlie. Bob's also sending reports to Charlie. Charlie is sending reports to employee ID number 4. So that's David. So Charlie reports to David. And then David sends reports to employee number 1, which is Andrew. Now let's imagine I wanted to show the results of the employee name and their report's recipient name. So I want to go from this employees table to something that looks like this on the right, where I have the name and then the person they're reporting to instead of just the report ID, which is the employee ID of the person reporting to. Technically, all this information is in this one singular table. So I can use a self-join to essentially make a copy, join it together in order to match the employer name or employee name with the report ID along with the employee ID. So let's break this down. Here again, we have the generalized syntax, and let's start swapping out the components given what we want to accomplish here, going from this employees to just the name of the person they report to. So what I'm going to do is first focus on the tables, because that's really what we're doing here. First things first is we have the main table. So we already know the name of that table. It's just employees. So if I take a look at my employees table, that's just the name of the table I'm working with. So I'm going to replace that with employees. And now it's time to select the first alias, which is table A. So what I want for my first column is the employee name. So I want to think of this as referring to the employee name based off the employee ID. So I'm just going to refer to that as EMP for employee. Then the second thing I want to do is focus on the person they report to. So for table B alias, I'll go ahead and label that, thinking of it as based off the report ID. So I'll label that as report. And then I need to decide what column am I going to join this on. Well, recall that the employee underscore ID column corresponds with the report ID column. The report ID column was just representing the employee ID number. And then the column we actually want to select happens to be the name for both this theoretical employees table and this theoretical report table. And this is the final syntax. So this will take our singular employees table and return back the results of one column of employees and then the second column of those same employees, but the person they happen to be receiving reports from. And in order to make sure you don't get two columns with name, we can always say that second column should be as rep. So essentially an alias for that second column. That way we don't see name. Instead we see name rep as shown here. So we want results showing the employee name and the report's recipient name. And again, make sure you kind of pause and make sure you understand the syntax and how we were essentially just swapping out the tables and swapping out the aliases. Let's explore a quick example on our own DVD rental database. Okay, here we are in PG Admin. Let's imagine that I wanted to answer the question, find all the pairs of films that have the same length. If we take a look at the film table, so select everything from the film table, we have the title of the film, and then if I scroll over, I also have this length column. So what I'm going to be doing is just focusing on that title column and this length column. And I essentially want to figure out what other films happen to match up together as pairs that have the same length. So if we take a look at Chamber Italian, for example, which is the first one that I got, notice here it's 117 minutes. So if I say select title length from film, where length is equal to 117 minutes, and run this, notice that there's, besides Chamber Italian, 4 other movies of Fair Prejudice, Graffiti Love, Magic Mallrats, and Resurrection Silverado that share the same length. But my final result, the way I want it to look, is to have 2 sets of titles and then their matching length. So essentially I want to have these paired off. Chamber Italian of Fair Prejudice, then Chamber Italian again of Graffiti Love, Chamber Italian of Magic Mallrats, and then Chamber Italian again finally with Resurrection Silverado. So how can we actually do this? Well, to do this, I would essentially need 2 copies of the same table. So this is perfect for a self-join. So what we're going to do here is forget about this where for a second, and I'm just going to run this. So we have select title length from film. First, let's decide how we actually want to format this. I'm going to pretend that I have 2 tables, film 1 and film 2, or F1, F2. So I'll say F1 title, comma, F2 title, and then I have to decide to grab the length from one of the tables. So we'll do it from F1. That way I can get something that looks like Chamber Italian, the Mallrat one, or whatever that film happened to be called, or Resurrection Silverado, and then 117 minutes. So it's going to do this for all possible pairs of films that have the same length. At least with the ones that, for the first instance, it found it in the title column. So then we're going to say, from film, as F1, and then we're going to do an inner join on film as F2. And this is where we have to decide what we're actually going to be joining on. So I'm going to say join film as F2 on, and I'm going to say grab film ID from F1. And I actually don't want to set it equal to F2 film ID. Instead, I want to say not equals to. But in order for this to make sense of why we're doing a not equals here, I'm first actually going to do it incorrectly with an equal sign. So if my F1 film ID is equal to my F2 film ID, and then I say and F1 length is equal to F2 length, notice what I'm asking here for. I'm basically just going to match up, for example, Chamber Italian with Chamber Italian again in the next table, or its copy. So if I were to run this, I'm just basically matching each movie with itself. So what I actually want to do is make sure that, for example, Chamber Italian's film ID doesn't actually match with any of the other film IDs in the table, but does happen to match with the same lengths. So we're going to say not equals to here. So that's the kind of fundamental difference in order to answer this question. So now when I run this, notice what happens. I get back Chamber Italians matched up with the other titles that happen to share the same length in runtime. So what I'm doing is I select film 1 title, film 2 title, film 1 length, from film as F1, inner join film as F2. So these are the aliases necessary in order to perform the self-join. And then on, in this particular case, in order to answer the query, I had to say not equals to the film ID. But I did want to make sure that their lengths matched up. And that's an example of a self-join using that DVD rental database that we've been playing around with. Okay, thanks, and I'll see you at the next lecture. Welcome everyone to this section on creating databases and tables. So far, we've really only focused on querying and reading data from an existing database and an existing table. We are now going to shift our focus to creating our own databases and tables using SQL commands. So for this section, we're first going to discuss a few theoretical concepts such as choosing a data type, primary and foreign key, as well as constraints. Then we're going to move into actual SQL commands to perform the creation of a database or a table using create, insert, update, delete, alter, and drop. So as I mentioned, we're first going to focus learning a few theoretical concepts, such as choosing the correct data type for a stored value and setting possible constraints on it, which means the first few lectures in this section are just going to be slide lectures. Then we'll also learn about things like primary and foreign keys. Once we learn these theoretical concepts, we'll move on to actually learning the SQL commands to implement them. Okay, with that being said, let's get started. I'll see you at the next lecture. Welcome back everyone to this lecture on data types. We already encountered a variety of data types that we've seen when calling off columns from an existing table. Let's quickly review the main data types in SQL, since when creating a table, we'll have to choose what data type each column should hold. So here are some data types, the main ones that we've already encountered. There's the Boolean data type, which is just true or false. There's character data types such as car or care, variable car, and text. There's numeric data types like integer and floating point number. And then there's temporal data types, things like date, time, timestamp, and interval, as well as timestamp with time zone. So we have these generalized categories that we're familiar with, and then we actually have data types within those categories. Some other not as common ones are things like UUID, or universally unique identifiers, which is essentially an algorithmically unique code in order to make sure you have a unique identifier for a particular row. Then you also have things like arrays, which store an array of strings, numbers, etc. You can also store things like JSON. There's HStore, which is a key value pair. And there's special types such as a network address and geometric data. Now, when creating databases and tables, you should carefully consider which data type should be used for the data to be stored. Let's imagine we want to store a phone number. And we start thinking, should it be stored as a numeric data type, such as a large integer? And if so, maybe what type of numeric? Should we be storing it as just a normal integer, a big integer, etc.? So we decide we have this task of storing a phone number. And we decide, should we store it as numeric? Well, first thing we should do is take a look at the online documentation for options. And if you go to that documentation page, you'll see a table that looks something like this, where you have the name of a specific data type under the general numerical data type categories. And we can see here we have a bunch of different options. We have small integers, which has a storage size of 2 bytes. We have integer, storage size of 4 bytes. Big int or big integer for 8 bytes. We have a general description for these, like small range, typical choice, and then large range. And you'll notice that as you get larger in these possible ranges, then the storage size becomes larger. And for a phone number, notice that if we just chose small int or small range integer, that actually doesn't have enough integers or digits for us to store a typical phone number. And then notice we also have other things like decimal, double precision, etc. These are things that are unlikely to be needed for a phone number. So you might be thinking, well, based on the fact that phone numbers can have extensions or maybe leading zeros, I'll choose something like big int or a large range integer, since it looks like these numbers are large enough for me to store a full phone number. Well, as I mentioned, based on those limitations, you may think it makes sense to store it as big int or big integer data type. But we should really be thinking about what is best for the situation. Remember, we're storing phone numbers, so why bother with numerics at all? We don't perform arithmetic with phone numbers. So it probably makes more sense to just use some sort of text data type, like a variable character data type, because you're not going to be adding phone numbers together or subtracting numbers from a phone number. Once you have a phone number, it's pretty much set. So it probably makes more sense to just store it as a text data type instead of having to even think about the possible range that is allowed for you if you go with a numeric data type. Welcome back, everyone. In this lecture, we're going to be discussing primary and foreign keys, fundamental concepts necessary to understand in order to create tables in SQL. Let's start with a primary key. A primary key is a column or a group of columns used to identify a row uniquely in a table. For example, in our DVD rental database, we saw customers had a unique, non-null customer ID column as their primary key. Unique means it has to be distinct for every row, and non-null means there must be an entry there for the primary key. Primary keys are also important since they allow us to easily discern what columns should be used for joining tables together. So let's see an example of a primary key. Here's a subset of a screenshot where we selected everything from a customer. Notice that we have this customer ID column, and pgadmin, when you grab table information, it will actually tell you if a column is a primary key for that table by specifying PK, or primary key. And so notice this is a unique integer, and it's also non-null, which essentially means that every row must have an entry here for customer ID. So this is a customer ID integer that uniquely identifies each customer. You wouldn't want to use something like the first name as a primary key because people can share the same first name. However, they cannot share this unique integer ID. So again, it's integer-based and unique. Later on, we're going to be learning about the serial data type, which is actually a way of automatically creating these unique integers for us as we enter more data into a table. Now let's discuss a foreign key. A foreign key is a field or group of fields in a table that uniquely identifies a row in another table. A foreign key is defined in a table that references to the primary key of the other table. The table that contains the foreign key is called referencing table or child table. The table to which the foreign key references is called reference table or parent table. A table can have multiple foreign keys depending on its relationships with other tables. So for example, recall in the DVD rental database payment table, each payment row had its unique payment ID, which was a primary key for the payment table, and it also identified the customer that made the payment through the customer ID. The customer ID within the payment table is a foreign key, since it references the customer table's primary key. So for example, let's check out and grab a subset here from the payment table. So technically we're grabbing all the columns, but the screenshot only shows a subset. Notice that for the payment table, we have this payment ID, and pgadmin lets you know that it's a primary key because it has PK there. So we have this payment ID, which is a unique identifier for every single payment row. However, you'll also notice that we have other IDs. These other IDs are foreign key references. Now, pgadmin won't directly tell you through a simple query call whether or not a column is a foreign key. We'll discuss how to figure that out in just a little bit. But here we can see we have these customer IDs, staff IDs, and rental IDs. Notice that within the payment table, it's okay if they're repeated because the same customer may have made multiple payments. So these foreign keys, the reason they're foreign keys is they're a reference to a primary key in another table. So customer ID is a foreign key within payment because it's a primary key within the customer table. Same with staff ID, it's foreign within payment because it's a primary within the staff table. Same with rental. And again, pgadmin won't alert you directly in a simple query call whether or not this is a foreign key. They'll only do that for the primary key. Now, you may have already realized that a primary key and a foreign key typically make good column choices for joining together two or more tables. When creating tables and defining columns, we can use constraints to define columns as being a primary key or attaching a foreign key relationship to another table. And we'll discuss this in more detail when we actually go over the create commands. However, I mentioned that in a simple query call, pgadmin only directly alerts you to something being a primary key and not a foreign key. I want to quickly explore the table properties that are available to us in pgadmin in order to get information on primary and foreign keys through the properties window, since we can't really see them directly through just a simple query call. Let's jump to pgadmin and show you how to understand the foreign keys that are present within a table. Okay, here I am in pgadmin. Recall that we had this example query select everything from payment, and I can see here that every single payment has a unique payment ID as a primary key. But also notice that we have customer ID, staff ID, and rental ID. And just from this query, we can't be 100% sure that it's a direct foreign key. Now, given how much we work with this DVD rental database, we do understand, and we're pretty familiar with the tables enough to understand that this customer ID, staff ID, and rental ID are foreign keys. But how do we actually understand that officially? How can we see the dependencies? Well, if you take a look at DVD rental, we can go ahead and expand schemas here. Give that a little time to load. And as that's expanding, what we're going to see is the public relationships. And then we have tables. So expand on tables. And then we have, scroll down. Let's go ahead and look at the table we're looking at right now, which is the payment table. And then we can expand on this and we can view the columns here. So we have payment ID, customer ID, staff ID, etc. Now, if something is a foreign key, that is technically a constraint on that particular column. And we're going to be discussing constraints in more detail in the next lecture. So let's expand constraints. And notice here we have certain keys. So there's actually a little key symbol. The golden key symbol is the primary key. So this is the payment primary key. So payment underscore P key for primary key. And notice it shows you that customer ID, rental ID, and staff ID are F keys or foreign keys, shown with another little kind of dual key symbol. So the constraints here will actually alert you to the fact that they are foreign keys within this table. Now there are a few more ways to actually review this information officially. If you want, you can actually select one of these foreign keys. Notice that it's highlighted. And once you select that foreign key, over here on your tabs, right now we're just on the actual query editor tab, go over to dependencies, click on that, and it will show you the dependencies for that particular column and alert you to what tables it's referencing. So notice here we have this customer ID, which is a foreign key within this payment table, and it's referencing, notice here, the customer ID, essentially telling you that under public schema, we have the customer table and the customer ID is that primary key we're referencing. So you can view that under dependencies. One other way to do this is if you right click on this, so right click on that constraint and select properties, it'll actually show you the properties and then you can expand on this to view columns and it will tell you that it's referencing customer ID. So it's referencing that from the public.customer table. So that's just yet another way to actually view what actual primary key it's referencing as a foreign key within the payment table. So lots of different ways you can review this information if you're dealing with a database instead of tables that you're not 100% familiar with. So again, let's imagine we just ran our query. We see these ID columns and we're not 100% sure whether or not they're foreign keys. We simply, underneath this little browser icon, we go ahead, view that table, view the constraints. Right away, this will tell you if they're foreign keys. If you want more details as far as what this actual foreign key is referencing, you right click, go to properties, go to columns. It'll tell you the schema dot table that it's referencing and then the column it's referencing within that table. Okay, so that's how you can figure out more information based off what's available to you in pgadmin for foreign keys. Primary keys, it's a little easier because any query should let you know if it's stated as a primary key constraint. Thanks, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on constraints. Constraints is the last thing we're going to learn about theory-wise before we actually head into using SQL syntax to create tables. Constraints are the rules enforced on data columns on a table. They can also be used to constrain everything in a table, and we'll talk about that in just a second. So constraints are used to prevent invalid data from being entered into the database. This ensures the accuracy and reliability of the data in the database. Constraints can generally be divided into two main categories. There are constraints on a column, which constrains the data in a single column to adhere to certain conditions. And then there are table constraints, which are applied to the entire table rather to just an individual column. So let's talk about some of the most common constraints used. The first one is not null. So the not null constraint is pretty self-explanatory. It's essentially telling you that a column cannot have a null value. Essentially, if you're going to enter data into this row that includes this column, it has to actually include a value for this column. So for example, if you're creating a table that happens to take in customer information and you always need an email from them, then you can say that the email column has a not null constraint, essentially saying that you are required to provide an email for this customer. Otherwise, it's an invalid row and it won't let you add it to the table. Then, another constraint that's really common is the unique constraint. This ensures that all values in a column are different. So a unique constraint could be used as something like a customer ID column because you want each customer ID to be unique. You wouldn't want to use a unique constraint on something like a first name column because people can definitely have the same first name. So unique, again, ensures all values in a column are distinct or different. Then there are primary key and foreign key constraints. We already learned about primary key and foreign key, but the way you actually define them when you're constructing your own table is you set them up as a constraint. So the primary key uniquely identifies each row or record in a database table, and a foreign key constrains data based on columns in other tables. So when you're setting up a foreign key, you'll actually also set up a relationship to another table you created. So we understand a couple of core concepts in theory. We understand data types, how to choose data types. We understand primary keys and foreign keys. And then finally, we understand the options for constraints. These constraint options are going to make a lot more sense when we actually program them out in the very next lecture. So don't worry too much about fully understanding them right now. Basically, I just wanted to introduce the keywords to you. That way they didn't seem to come out of nowhere in the next lecture. So with all this under our belt for theory, we're ready to begin using SQL syntax to create tables. So let's go ahead and do that, and I'll see you at the next lecture. Welcome everyone to this lecture on the create keyword. Let's now learn the syntax to create a table in SQL using this create keyword and the generalized column syntax. So, when you're creating a table, this is the full general syntax layout, and we're going to focus on just a couple of things here, and then we'll walk through some examples in PG Admin. But let's go over the general syntax components. First, there's the create table, and then you choose whatever table name you want. So you would say something like create table payments or create table customers. Next are the columns that are within that table, and you'll choose the column name, then the data type for that particular column, and then you'll add in any column constraints. And you just have this almost as a list of different columns. Something to pay attention to are the fact that you use commas to separate out these columns. A really common mistake for beginners is they forget this comma at the end, and then you'll get some sort of weird error that's hard to actually diagnose. So again, just remember there's a comma there when we're dealing with the actual columns. Next, you add in any table level constraints that you want. So you can list off different table constraints. And we talked about those options in the constraints lecture. And then, in case you have some sort of relationship to another table, and you can inherit from an existing table. Now we'll talk about things like table constraints and the inherits command later on. For now, I really just want to focus on creating the table and setting up your columns. So we're going to follow along right now for this lecture with what I'm going to call common simple syntax, which is just creating the table and then adding in your columns. Let's work through a very quick example, and then we'll go over to PG Admin and actually code it out. So for an example syntax, you would keep create table. Those keywords don't change. And then you decide on a table name. So let's go ahead and make up a players table. Then we have to decide what columns are going to be in our players table. Typically, what you're going to do first is you're going to choose a column to be a primary key. Typically, each table should have a primary key. Obviously, this may change depending on your circumstances, but let's go ahead and go with that. So we're going to have a player ID as the column name. We have to choose a type. And almost always, especially with PostgreSQL, when you're trying to think of a primary key, the type should be serial. So I actually want to focus in on this serial data type because it has some special properties. So in PostgreSQL, a sequence is a special kind of database object that generates a sequence of integers. and a sequence is often used as a primary key column in a table. So what serial is going to do, it's going to create a sequence object and set the next value generated by the sequence as the default value for the column. And this is perfect for a primary key because it logs unique integer entries for you automatically upon insertion. So that means as you're inserting more data into this table, you won't actually need to worry about providing a unique player ID yourself. Instead, serial is going to do this for you, which makes sense because as you insert data, you're probably not going to know what actual player ID you're on as far as the integer count goes. So serial takes care of this. So what's also nice about serial is that if a row is later removed, the column with the serial data type will not adjust. It's not going to reformat everything in the serial. Instead, since it's not going to adjust, it's actually going to mark the fact that a row was removed from the sequence. For example, in this primary key column, as you're inserting players, you may see something like 1, 2, 3, and let's imagine we inserted 4, 5, 6, 7. And then later on, you decide to delete row number 4 because that player maybe left your team. What's nice about this is serial is actually going to show that gap as the primary key. It'll show 1, 2, 3, 5, 6, 7, which means as you, as a user, go back to that table and see that you're missing number 4 from the primary ID column or primary key column, you know now historically that row 4 was removed at some point. So serial takes care of a lot of problems for us automatically. It makes sure that each of these is unique because it's a sequence that keeps adding 1 based off the previous value, and then we ourselves, as we insert data into this table, don't need to even worry about providing a value for the primary key column. Okay, so you may already be familiar with this table. We mentioned it in the data types, and you'll notice that there's actually options for different types of serial. There's small serial, which is just 2 bytes, and it goes from 1 to about 33,000, so 3,000 to 767. And then we have serial, which is 4 bytes. It goes to a larger value, and then big serial goes to an extremely large value. So you can choose which one of these is appropriate for you, depending on how large your table is going to be. So we'll just go ahead and choose serial. Again, you could have chose small serial or big serial, but we'll just do serial as our data type because this is going to be our primary key. Because this is our primary key, we actually type that in as a column constraint. So we set the table to verify this is a primary key. And then finally, let's go ahead and add in one last column. So let's go ahead and put the age of the player. So we have to choose a type for this. Again, you can go back to that table in the documentation, decide what types are appropriate. So if we take a look at this, maybe we decide that a small integer is appropriate. We don't need such a huge integer value range for ages, especially for people, because people can only go from 0 to a little above 100. We don't need the integer to go to some huge large number. So we'll go ahead and say that the data type is a small integer, and then the column constraint can really be whatever you want. But let's imagine that for some reason, our league that these players are playing in is constrained by the age. Let's say players that are over 18 can no longer play in this league. So because of this requirement, we actually need to make sure that we know the age of the player, in which case we'll want to make sure that a column constraint could be something like not null, meaning that if you're inserting a player into this table, you cannot leave the age blank. Otherwise, the table will reject the new entry. Okay, so this is an example syntax of creating just a very, very simple table. So let's go ahead and actually explore some examples in pgadmin and typing this out. All right, here I am inside of pgadmin. To begin, I want to make sure we create these tables in a brand new database. That way we don't accidentally contaminate our DVD rental database. So what I want to do is, if you already have a query editor open, which you may have as you're following along with this course, you'll notice that it's open as a tab here. Note it says DVD rental, Postgres, etc. Go ahead and right click on this and just click remove panel. And it's going to ask you if you want to save any changes. We don't need to worry about that, so don't save. And that way we make sure that we don't accidentally run this query editor in DVD rental. The next thing we're going to do is we're actually going to create a new database. So underneath PostgreSQL, underneath databases, right click, go to create database. And then we're going to go ahead and you can really call this database whatever you want. I'll call it learning. And again, it's really up to you, but just for learning how to create databases and tables kind of makes sense. So you don't need to worry about changing anything else. Go ahead and click save. you should see learning appear here. Go ahead and click on it. And then just to make sure everything's working, after you click on it and you've made a connection, just hit refresh. And then we should be good to go. So after this, I'm going to right click on learning. And then I'm going to open up my query tool. And the query tool can not only be used for getting information from a database, but we can also run SQL commands to create tables from here. So that's what I'm going to do. And just to confirm that we're on learning with this query editor, go ahead and take a look at your tab here, and you should see learning here underneath the tab. Okay, so now that that's done, let's go ahead and create our table. So the first table we're going to create is just an example account table. So we have our first keywords, create table, and let's just say the table name is account. And then we have open and close parentheses. And here, over multiple lines, is where we can add in the actual column names. So I'm going to have a user ID column, and I'm going to set this as serial. And because it's going to be serial, the constraint I'm going to set on it is primary key. So this is going to be a primary key identifier that is automatically set up for us so that as we learn how to insert information into this table, we don't actually need to worry about inserting a user ID. Serial will take care of it for us. And that'll make more sense when we talk about the insert command. So that's one column. Don't forget to put in your comma. And then we'll have a username. And technically, you don't really need to worry about indentation or spacing. But just to make these line up so it looks a little nicer, we'll go ahead and do that. And then we're going to have just this be a variable character. And when you're using variable character, you have to pass in the limits of how long you allow this to be. So this could be a limit of, for instance, no more than 50 characters inside of the username string. And we want to make sure that each username that is set up here is actually unique. That way we don't accidentally have people with the same username. So we can set it up to be unique. The other thing we should probably set up here is that if you're setting up an account with us, we can't just have your username be blank. So we also want to make sure that it's a not null constraint here. So we have that. The next thing I'm going to set up here is a password column. So we can store their password. We'll have this be variable character 50 as well. And passwords, let's say we don't need to worry about them being unique. People can maybe have the same password, especially if this is not really a security threat. But we should make sure that they actually have a password. So we'll again say it cannot be null. And obviously there are things like security concerns that we're not really taking into account here when it comes to passwords. So very, very simple database, really just learning the syntax here. Let's go ahead and provide an email column. We'll have this be variable character as well. Let's say emails are typically longer than, let's say, a 50 character limit. Some people can have really long emails. So we'll go ahead and choose something like 250 characters available. And again, we want to make sure that there aren't shared emails. So the emails, just like a username, should be unique. And it should also be not null. The constraints is really going to depend on your specific situation. So keep that in mind. Every single table and database has its own unique situation. So I can't give you some general rules for what constraints you should provide on your own columns because that really depends on your business situation. And finally, let's go ahead and create some timestamp columns. We want to keep track of when an actual table is, or a row is created, like an account is created. So we'll say created on, and we'll have this be a timestamp. We'll have that be not null. And let's go ahead and keep track of when the person last logged in. So we'll say last login, then also have that be a timestamp. So if we scroll down a little bit here, just to see the parentheses that closes this all off, notice my very last column didn't actually need a parentheses because I'm not adding anything after that. And also notice that I'm not going to go ahead and say any constraints on last login because what I want to make sure that is even if you have just created your account, you won't really have a last login, which means if I said not null here, that may have created some sort of error. So created on should definitely be not null, but last login, I don't want some sort of error occurring if the person created their account but doesn't have a last login because they just created their account. So that's why there's no constraint here on last login beyond just the data type having to be a timestamp. Okay, so here's our create table account. Let's go ahead and run this. So when you run this, it'll say something like create table, query returned successfully. The data output shouldn't show anything because we're actually not asking for anything here. And if you see explain, pretty much all this should be blank. Keep in mind though, you can only run this one time. So take a look here underneath learning, schemas. We have the public schema, and then we have now tables. Expand on that, and you can see this new account table. So this account, if we expand on columns, I can see the columns I created, and I can actually also see some of the constraints I created. So notice here now we have a little primary key constraint, and on the account email key, it has 1 here, basically indicating that there was a specific constraint there. Okay, so we have that all set up, ready to go. Something I want you to again note, which is a really common error, is I'm going to induce an error by clicking execute again. If you click execute again, the error is actually relatively straightforward. It says relation account already exists, which makes a lot of sense. You don't want to accidentally create the table account again and then overwrite an entire table. So instead, PostgreSQL is going to just tell you, hey, you can't create that table. It already exists. Later on, when we learn about things like the alter command, we will be able to alter and edit existing tables. So we have this account table. Now what I want to show you is the ability to create another table and then link them through a foreign key. To show you this, we're going to start by creating 2 more tables. So we have this person with the account. Let's go ahead and create a job table. So let's say certain people can be assigned jobs later on. So we're going to say create table, job. And this job table will have a job ID column. And this is going to be a serial column, primary key, because it's a unique identifier for the job. And then the job will have some sort of job name or job description. So we'll say job name is the other column. We'll make this variable character. Let's give it a limit of 200. And then these should be unique. That way we don't accidentally have 2 jobs with the same name. And we can't have an empty job. So we can't just have a job ID with no job name. So here's our create table. Very simple for the jobs. Let's go ahead and run this. We should get back create table, query returned successfully. Remember, you can only run this one time. And now what I want to do is I want to create a table that references both the account and the job. Basically, it's going to be an intermediary table that connects someone's account to their specific job and when they were hired for that job. So this is going to be the table that shows us how to actually reference a foreign key. We're going to say create table. This is going to be the account job table. And it's going to have a user ID column. And this user ID column should be the same as the user ID in the account, which means it's going to be an integer type. Notice that I'm not saying serial. Serial should only be used as a primary key for the table that it's in. When you're using it to reference in another table, it's just going to show up as a normal integer because serial is really just a sequence of integers. So because this is going to be a foreign key reference, I'm just going to say that my user ID is an integer, and then here comes the keyword that references. And I need to tell it what column and what table to reference. So I pass in the table name, and then in parentheses, I pass in the column name inside that table. So recall, inside of this account, I have a user ID column. So the user ID column inside the account table will be the reference or foreign key reference for the user ID integer inside of the account job table. Then we're going to say comma, and let's do the same thing for job ID. So we will say job ID is also going to be an integer that references from the job table, the job ID column. And then finally, let's go ahead and add in some column that basically tells the person when they were hired for this job. So let's say there was a hire date, and I'm just going to have that be a timestamp. If you want, you can optionally add in things like it has to be not null, but just keep things simple. I have this hire date. Let's go ahead and run this. So I'm going to expand this a little bit, run this, and we should see query return successfully. So now I have 3 tables. We come back here. Notice that right now it says tables 1. That's because I need to refresh this. So typically you're going to need to refresh every time you create a new table. Go ahead and refresh. That lets the database essentially know, okay, here are now the information on the 3 tables. I have job, and account. Account was that first table we created. And if I take a look at account job, taking a look at the columns, I have user ID, job ID, hire date. Then we have these constraints. And notice now we see essentially information that we have these foreign keys. You can check out our lectures on primary keys and foreign keys to refer to how you can confirm those sort of connections. Okay, so that's the very basics of creating a table with columns that have both primary key and foreign key references. Coming up next, we're going to learn how to insert information into the table. I'll see you there. Welcome everyone to this lecture on the insert command. As you may have already guessed, insert allows you to add in or insert rows into a table. The general syntax looks like this. We say insert into, decide on the table name, and then also clarify which column values we're going to be providing. And then we say values and add in a list of values. Keep in mind you can also have a syntax for inserting values from another table. This looks kind of similar. We'll say insert into table, decide on the columns we're inserting to, and then we say select those matching columns from some other table where some condition happens to be true. So something to keep in mind, especially for the previous statement of inserting from another table, the inserted row values must match up for the table, including constraints. So if one of your constraints was that the column is not null, then you must provide a value as you insert. Otherwise, you'll get an error. If you're grabbing information from another table and inserting it into your table that you're currently using, then you must make sure that those actual columns also match up for things like data type. Another thing to keep in mind is that the serial columns, especially for those primary keys, they actually do not need to be provided a value. Recall that serial is a sequence, so it's going to automatically update the next available integer for that row. Okay, let's go ahead and actually work through some syntax examples using pgadmin. All right, here I am inside of pgadmin. Let's go ahead and recall what we actually used for our account table that we created previously. To do that, I'm going to, in my query editor, say select everything from account. Run this, and you shouldn't get back any data because we haven't inserted anything yet. And I can see here I have user ID, username, password, email, created on, and last login. Recall that user ID is serial data type, so I don't need to worry about providing that. And also recall that the last login column didn't have any constraints, so I don't need to actually provide one of those. Everything else, I believe, had some sort of not null or unique constraint, so we will need to provide. So let's go ahead and show you how you can insert into this table. We're going to say insert into, and then the account table name, which was just account, and then the columns we're going to provide. We're going to provide a username, a password, an email, and then we'll also say created on. And then after this, we're going to say values, and then we provide the list of values. So let's go ahead and choose a username. We'll go ahead and have the username be Jose. The password, typically you don't save passwords as strings in a database. There'll be a hashed version of a password, but just for learning syntax, we'll say that Jose's password is password. The email, we'll go ahead and have this be jose@mail.com, just the made-up address. And then make sure we say created on, so check for that typo there. So created on, make sure that matches up. And now we're just going to provide a timestamp. And in order to save time, instead of providing a long string code for a timestamp that includes the date and the time, I can actually use from our timestamp lectures the current timestamp functionality. So I can say current _ timestamp. And you can review the documentation and our timestamp lectures for a full list of these sort of timestamp function calls. So this is just going to insert those values here into the table. So let's go ahead and run this. And you should see something that says query returned successfully, etc. And under data output, we'll still see the same blank because we haven't actually asked again for the information from account. So let's go ahead and delete this. And then say, select everything from account. Run that, and notice we get back user ID 1, so it's automatically created for us. We have Jose, password, jose@mail.com, and then we have the created on. And notice the last login is currently null. So we were able to successfully insert into this new table. Now let's go ahead and practice inserting into the job table. So recall the job table, if we take a look at it here, has the columns job ID and job name. Recall job ID was serial, so I don't need to worry about actually providing a job ID. So what I'll do here is I'll say insert into, and then we have the job table. The columns I'm going to insert is just the job name. So what I'll do here is say job underscore name. Then I'll say values that I'm going to insert here. And job ID is created automatically through serial. So I just need to say job name. Let's go ahead and have the job name be like an astronaut. So we'll say astronaut. Go ahead and run this. We get back query returned successfully. Let's check on that by saying select everything from job, run it, and now I can see I have a job ID 1, job name astronaut. And let's add one more job just so we can explore this job ID. So we'll say insert into job, and we're going to insert a job name. And we'll say values. Let's go ahead and have it be president. So we'll say president as another job, run that again. And if we check out the table again, select everything from job, notice that the job ID is automatically being increased for us, which is really nice. Okay, so we have this job table with some job options, and we have the account with basically kind of a fake entry into the count. Let's go ahead and finalize everything by actually doing one connection for an account job, essentially assigning the account I've made myself to a job. That's going to be a little different because we have that foreign key set for us. So what we're going to do here is we'll simply say, like we did insert into, we will say account job, pass in a user ID, a job ID, and a hire date, and expand on this just so we can see the whole thing. Then we'll select the values we're going to insert, and we'll say user ID is 1 because that matches up with the first person we made in the account table. We'll go ahead and have him be an astronaut, so that's job ID number 1. And then the hire dates, let's just say current timestamp. So we run this. We get back query returned successfully. So let's go ahead and delete this. Say select everything from the table, which was account job. Run that, and I can see user ID 1, job ID 1, and a hire date. Let's go ahead and show you what happens if we try to insert someone whose user ID doesn't exist. So I'm actually going to do Control Z a few times to get back this command. So just Control Z a few times should bring you back to insert into account job. And I'm going to insert, let's say, user ID 10 with job ID 10 at my current timestamp. Currently, we don't have a user with user ID 10, and we don't have a job ID with job ID 10. So when I try to run this, notice what happens. We get this error. And the reason we're getting this error is because it's violating the foreign key constraint. So just like we have to provide information for things that are not null, we have to make sure that when we're inserting something that has a foreign key constraint, that it actually exists in the other tables. This is the exact kind of behavior and error you want. Otherwise, we're doing some sort of link that doesn't actually exist. There was no user ID of 10. There was no job ID of 10. So keep that in mind. These constraints will do things like stop information being inserted into it if it actually violates the constraint. Okay, so that's the details for how to insert data into a table. We'll see you at the next lecture. Welcome back, everyone, to this lecture on the update keyword. The update keyword allows for the changing of values of the columns in a table. The general syntax is as follows. We say update, then what table we want to update, and then we can say set column equal to, and then some apparent value that we've chosen for that column. And then we can also specify conditions for where the update should occur. So let's show you an example. We can use that account table we created earlier to say something like update the account table, and then set last login column equal to the current timestamp, where the last login is null, which basically says if there is a null value in the last login, go ahead and update all those values to be the current timestamp. You can also reset everything without any where condition. So if I wanted to just overwrite and update all the last login entries, I could just say update account, set last login equal to current timestamp. I could also set everything based off another column. So we also have the created on column. I could just say update account, set all the values in last login equal to created on. I could then also add in a where condition on top of this. We could also use another table's values. This is sometimes known as an update join, even though it doesn't use the join keyword. So the way this works in general syntax is we choose the table we're updating, such as table A, and we say update table A and set the original column, which is part of table A, equal to some new column part of table B. From table B, where table A.id is equal to table B.id, which is essentially where that joining is taking place. So we just figure out some key to match these two tables on, and then we say set the original column within table A equal to table B.new column. We can also return the rows that are affected. So if you just run one of these update commands, you don't see any results. But if you do want to see particular columns that were affected, you can set the command, something like update account table, set last login column equal to the created on column, and then you can say returning and choose the columns you want returned, and it's going to return the rows that were actually affected. And you can return all the columns or a subset of columns. It's really up to you. Let's go ahead and explore this further in PG Admin. All right, to begin with this, I'm going to take a look at the account table we set up earlier by saying select everything from account. Notice I'm connected to that learning database. And so far, if you've been following along, you should just have one entry in this account table. If you have more than one, that's okay. So we have this username, password, email created on, and currently our last login is null. So let's go ahead and change that a couple of different ways using update. So one thing we can do is set it to some sort of value, just all over. So I can say update account and then say set last login, and I could set it to the current timestamp. So I could say something like set it to current timestamp. I run that, and notice it doesn't actually give you an output, so I'll have to ask again to select everything from account to see the change. Run that, and if I scroll over, now I can see the last login matches the current timestamp for when I ran that. Let's go ahead and just have it match the created on column. So to do this, we're going to say update account and say set last login equal to created on. Run that. So it looked like that worked. Let's go ahead and check on that. Select everything from account. Go ahead and run this. And now if you ran that, you should see these two match exactly down to the sub-second because it's directly lifted off the created on. And finally, let's explore how we could do an update based off two tables. So to do this, we're going to explore that job table we created. So again, we have this job ID, job name, and then recall that not only do we have the job table, but we also had, if we expand on this, the account job table. So we're going to say account job, run that as well. And it looks like we have a hire date. Let's go ahead and change the hire dates based off another table. Now, the procedure here is really just for syntax purposes. The actual logic behind this won't make too much sense as far as why anyone would want to change the dates for this hire date based off another table. So just keep that in mind. This is really just for a syntax example. Okay, so how we're going to do this is I'm going to update from this account job table, and I'm going to set the hire date equal to, and let's use the account table, and let's use the created on date from that. So we'll say update account job, set hire date equal to account dot created on from the account table. So we have to specify what's the other table. And then we're going to do the following. Essentially, this is where the join comes in. We're going to say where account job dot user ID is equal to account dot user ID. So we run this. It was successful, which means if I were to select from account job, notice here the actual timestamp. Let's just go ahead and take a look at the subseconds. So 1909. And now let's take a look at the account. And it should be the exact same 1909. So again, that's the syntax for updating based off the results from another table. Very, very useful to know that. In this particular example, maybe that logic of the reasoning behind it didn't make too much sense on why you would want to do that. However, that was really just for the syntax example. So again, you update table A, set what you actually want to update from table B, and then show where you're actually matching that up, which is why this is known as an update join, even though we're actually not using the join keyword. And then finally, I want to just show you the returning keyword. Let's go ahead and go back and update our account table. Let's just set the last login equal to, again, current timestamp. Essentially just resetting it a little further into the future. So we'll update account, set last login equal to current timestamp, and then I can say returning, and I can return something, basically whatever columns I'm interested in, such as email and let's say last login. And let's also grab in the created on, just so I can compare them. We run this, and that successfully ran. And in addition to that, it returns back whatever columns you were interested in. That way you don't need to do that select second step just to clarify or double check that your results went through. Okay, that's it for the update command. I'll see you at the next lecture. So pretty straightforward. That's the syntax for the delete statement. Thanks, and we'll see you at the next lecture. Welcome back, everyone, to this lecture on the alter clause. The alter clause allows for changes to an existing table structure. It has lots of use cases, such as adding, dropping, or renaming columns, changing a column's data type, setting default values for a column, and even renaming a table. Let's look at just a few examples for the general syntax for these cases. The general syntax is alter table, table name, and then some sort of action call. For example, if you wanted to add columns to a table, you would say alter table, table name, add column, the new column name, and then specify a data type. You can remove columns by saying alter table, table name, drop column, and then the column name you want to drop. You can alter the constraints of an existing column by again using alter table, table name, alter column, the column name, and then you can do things like set a default value. You can drop the default value. You can remove or add in a not null constraint, such as setting a not null constraint to add one in. You can drop a not null constraint. So let's go ahead and explore some examples, as there's lots of things we can do with this alter table command. Okay, here I am in PG admin. Since we're going to be doing so much altering and editing to a table, let's go ahead and create a new table first. We'll say create table, and we'll have just this table be called general information. And let's go ahead and have just a couple of columns here. We'll say an info ID column, which is going to be serial and based as a primary key. Let's have something else called title. This will just be like the title of some information. Say 500 characters max. And let's say for now, it cannot be null. And we'll add in one more column. Let's go ahead and have this be some person the information is related to. Again, variable character, we'll say 50. And let's have it be not null as well as unique. All right, so very basic table here. We'll go ahead and run this. Okay, so the table's created. Let's select everything from that table just so we can see the columns. So select everything from the information table. We have info ID, title, and person. Let's do a couple of things first. Let's go ahead and rename this table. So the way we do this is by saying alter table. We choose the current name, which is information, and then we say rename to, and this will change the table name to something else. Let's go ahead and call this table new info. We run this and we successfully alter the table, which means if I were to try to select from the information table, I get information does not exist, which means I need to use the new name, which is new info. And again, we get back this empty table. So that's how I can rename the table. If I want to rename just a column, I can do this. I can say alter table, new info, rename column. Let's go ahead and rename the column. So the way this works is we say rename column person to, and then the new name. Let's go ahead and say people. Run that. And if we select everything from new info, I see now person is people. So obviously a lot of things we can do here with this alter table command. The next thing I want to do is show you how you can use the alter command in order to alter constraints that already exist on certain columns. But to do this, first I want to show you how we could try to insert data into this table. So I'm going to say insert into new info, and I want to insert, let's say, just a title. Recall that people was also not null. So I'm actually not going to provide people on purpose here. We're going to say values, and let's just have title be some new title. And if I were to run this, I get back an error saying null value in column people violates not null constraint. Okay, so we have two options. Either I can add in people and then add a value for it, or I can try to remove this not null constraint using alter table. Obviously, that affects it permanently for the table on a table level, but this is just to show you the alter command. So I'm going to say alter table, new info, alter column, people, and then we're going to drop the not null constraint. If I wanted to set a constraint, then I would use set, and that adds a constraint. If you want to remove a constraint, you use drop. And recall, this not null can be anything. It could be dropping the unique call, the not null call, any sort of constraint here. Okay, so let's go ahead and run this. Okay, so I successfully altered that table. Now what I'm going to do is if I take a look at my query history, I can actually grab that old query of insert info. So let's go ahead and copy this. You can also, I'm pretty zoomed in here, might make it look a little strange, but in yours, you should see insert into. Go ahead and copy this. You can even copy it directly into the query editor. So I'll just click that. So we're trying to now insert into new info, title, values, some new title. Let's go ahead and run this, see if it works this time. And notice that it was able to work because I had removed that not null constraint. So if I select everything from new info, run this, we're able to add in some new title and keep people as something null. If you ever get confused or stuck or have trouble remembering what the actual calls are for the alter table command, you can always go to the documentation and look up alter table, and it has a whole synopsis of the different variants you can use, such as rename to table, etc. We can also show you different actions that are available, dropping columns, adding columns, altering columns, etc. So lots and lots of different options here and examples. And if you start scrolling down, it has even more detail on each of these commands, such as alter constraint. There's also things like dropping constraints, etc. So lots of different options here. It's all for you. It's all here for you in the documentation. Okay, thanks, and I'll see you at the next lecture. Welcome back, everyone, to this lecture on the drop keyword. Drop allows us to completely remove a column from a table. In PostgreSQL, this also automatically removes all of its indexes and constraints involving the column. So it'll remove things like check constraints, not null constraints, unique constraints, everything that's associated with that column. However, what it does not do is it does not remove columns used on other things that are dependent on it, such as views, triggers, or stored procedures. If you do want to remove a column that has those dependencies for views, triggers, and stored procedures, which we're going to talk about in more detail later on, you can add in an additional cascade clause in order to just remove that column and those associated dependencies. The general syntax for a drop call, for dropping a column, would be alter table, table name, drop column, and then the column name. To remove all those dependencies I previously mentioned, you can say alter table, table name, drop column, provide the column name, and add in the keyword cascade, essentially cascading that removal to all those dependencies. Now, if you try to drop a column that does not exist, you'll get an error in PostgreSQL. So it's really common to add in an if exists keyword clause before the column name in order to avoid the error. So that way it only drops the column if that column name exists in that table. If you want to drop multiple columns, it's almost like adding in multiple column values. You simply say drop column 1 name, comma, column 2 name, comma, etc. Okay, let's go ahead and see a quick example of this in pgadmin. All right, here I am in pgadmin. Recall that we have this new info table that we created when playing around with the alter commands. Let's go ahead and drop the people column. So we'll do the following. We're going to say alter table, new info, and we're going to say drop column, and then say people. We run that, it worked out correctly, which means if I now select everything from new info again, run it, I don't have that people column anymore. Let's see what happens if we look at our query history, try to run that drop again. So I'm going to copy this to my query editor. This is the same thing we did last time. Alter table, new info, drop column people. Go ahead and try running this again. You'll notice you get an error. It says column people of relation new info does not exist. But if I add in if exists right before people, what it's going to do is going to attempt to drop the column only if it exists. And instead of getting an error, you'll get back a notice saying column people of relation new info does not exist, skipping alter table. And then I'll say query returned successfully. So instead of an error, it just gives you this message. All right. And that's basically all there is to dropping columns. Pretty straightforward exercise. Thanks, and I'll see you at the next lecture.